Firstly, let's deep dive into the model 1. We use a faster RCNN model pre-trained on COCO dataset and fine-tuned on some of the official PyTorch datasets and wide percent dataset, as you can see in the images below. Now, why do we use the faster RCNN model? Firstly, it is because it finds the region proposals and bounding boxes in a very fast manner. Secondly, it works with the input images of arbitrary sizes, whereas most CNN-based models adjust the image to a specific size. This is the architecture of the faster RCNN model, in which input is passed into VGG16 framework to get feature maps, which are used to find the regions of interest. The regions of interest are then passed on to the softmax classifiers to get the bounding boxes and finally a cropped body image. We then apply OpenCV Cafe model to get the face images if the face is visible in the frame. Results of the proposed model with some benchmarks is shown here. It is about 1.5 times faster than the state-of-the-art RCNN and 20 times faster than model in a research paper of RCNN, with a very less considerable increase in miss rate. These are the results of an image from a mall to extract the body cutouts from it. As you can see, we have got 5% cutouted from the mall environment as shown in the figure. Moving on to the OpenCV Cafe model, it extracts the face bounding boxes as seen here. It basically extracts the face if the face is visible in the frame. Now my colleague will further elaborate on model 2.
The second stage of our pipeline is to pass the crop body and face images through model 2, that is real SRGAN for super resolving. The real SRGAN uses the same architecture as that of the ESRGAN except that the pixels are unshuffled before feeding into the ESRGAN network. It reduces the spatial size and increases the channel size. Benefits of using results. We tried several super resolving techniques like SRGAN, bicubic, ESRGAN,
Excuse me, Saini, actually
real
your
SR.
voice is getting echo.
Sorry, sir, now is it clear?
I think better.
Okay. So we tried several super resolving techniques like SRGAN, bicubic, ESRGAN, real SR, and real SRGAN, out of which real SRGAN was found to be the best at capturing real-time textures. This is because in its discriminator network, it applies nth order degradations to replicate real order distortions. As a result, it could reproduce the original quality of the image to a greater extent. Apart from the advantages, there are several challenges of using real SRGAN. One major limitation is that when the dimension and quality of the original input images are very less, for example, if the dimension of the input image is around 24 cross 60 pixels, then the model tends to smoothen the edges. As a result, it might generate undesired textures in the image. Though the real SRGAN tries to reduce the artifacts, it fails if the degradation is very high. It may generate a twisted line effect, and it might also generate some textures on its own which might not be present in the original image. The twisted line effect can be seen in the blue building image that has been in the slide, and the generative artifacts effects has been shown in the gray image that is there on the slide. We can see some of the results of model 2. We can see that the model 2 is performing very good in enhancing the quality of body images as well as face images. Now, my colleague will elaborate on model 3.
Hello, am I audible? So this is the Model 3 age and gender detection. So Model 3 was built to predict the age and gender of the person. The main purpose was to extract the feature from the CNN layers, and we used the famous architecture as well as the Scratch implementations to achieve the same. This is the architecture of the Model 3. So we are receiving the super resolved body and facial images from the Model 2, and we pass them through two different convolutional layers specially selected from them as the feature extractor. After receiving feature vectors for the face and the body images, we concatenate them. Then we use collaborative learning explained later to predict age and gender from the concatenated vectors using two different fully connected layers trained from scratch. But why we are using face and body images? In a literature survey we did, we found that very less research has been done on age and gender prediction using body images, and not many open source body image datasets with age and gender annotations were available. So most existing work are using facial images for prediction. The input for our problem statement was low resolution surveillance video feed. The faces of the people would not necessarily be visible as if we consider only so only if we consider the facial images, we would be completely ignoring the body images and the clothing, which which could help in predicting the age and gender to a great extent. So this is the body only model. The body only model we trained some state-of-the-art CNN architectures like VGG, ResNet 18, ResNet 50, MobileNet, but we achieved the best accuracy with a scratch model that we defined here. The reference for this architecture for the scratch model was taken from a research paper on PETA dataset only, and these are the default hyperparameters that we use while training. This is the best accuracy that we received from the scratch model. It's 66.8%. The face only model. So we did similar work for the face only model as well. We trained different models, checked their accuracy for the combined age and gender prediction, then extracted the convolutional layer part of them of the best model to use in our model. For the face data, we use UTK dataset. These are face only models for age and gender prediction. Though this mentioned that FaceNet has 35.4% accuracy, that's the best we received. But in the final code submitted, we used VGT16 because of the time constraint, we were unable to implement the FaceNet model in our final code. Now my colleague will explain the combined model working.
As mentioned previously, we are using both face and body images for age and gender prediction. Thus, we have used two CNN-based feature extractors, a face-only model and a body-only model, which have already been elaborated. The feature vectors from the two are concatenated, and the final feature vector is passed through the linear layers for prediction. We are simultaneously predicting the age and gender of the person detected. To enable collaborative learning, we are using a special weighted loss function, whereby equal weights are assigned to the two losses initially, and if the accuracy of one of the predictions exceeds a threshold of 70%, the weight for that prediction layer's losses is reduced to 0.1, and for the other loss, it is increased to 0.9. Further talking about the future improvements that can be done with the entire pipeline, the most difficult part was finding an appropriate dataset relevant to the problem. There were a very few open source face and body images datasets available with both age and gender annotations. Due to time constraints, we couldn't create one of our own and would like to work
Time.
upon it. Can I just continue for these 3 points?
Yeah, please. End up in
Okay.
1 minute.
Okay. So for the model 1, we want to improve the human body detection from the low resolution video feed by trying more architectures. For model 2, we want to fine tune more state-of-the-art architectures and customize it for generating better super resolved images and avoid smoothening and distortions. For model 3, we would like to augment the data appropriately, try more architectures, and further improve the weighted loss function for collaborative learning to improve the accuracy for age and gender prediction. With this, we come to the end of our presentation. Thank you.
Okay, judges. Now we can move on to Q&A session.
Okay. So, can you go to the collaborative learning slide, please? Okay, so this is the loss function that you have used. So the weighted loss you have used, and you were explaining about alpha being 0.9. I missed that part. Can you elaborate that again? Shreya, right?
Yeah, it was me. So basically,
Yeah.
what we have decided is, what we have done is that if the accuracy of say gender prediction exceeds a random threshold of 70%, then the weight for the prediction layer loss of gender will be decreased to 0.1, and for the loss for the age prediction, it will be increased to 0.9. And this the choice of 0.9 and 0.1 is because we wanted the model to learn faster.
Vinod, any comments from your side?
Hello. Hello.
Yeah, you're audible. You're audible.
It's audible, right? Um, yeah, Deep, then can you explain the same about one more time? So I couldn't hear clearly. This collaborative, this one loss, how was it done?
Yes, sir. So, suppose the accuracy for gender prediction comes out to be greater than 70%, then the weight alpha for the gender loss, it will be decreased to 0.1. Initially, both are alpha is 0.5, so 1 minus alpha is also 0.5. So then alpha is decreased to 0.1, and 1 minus alpha is increased to 0.9. We'll be assigning more weight to the loss for age.
Okay, so you will be assigning more weight to age.
Yeah, if the accuracy for gender comes out to be greater.
Okay, is it
And
some kind?
why are you keeping the threshold as 70%?
So that's an arbitrary value that we decided.
So is it some kind of focal entropy, like providing more weights to the less number of examples?
Sir, I would like to tell on that. We decided 70%. Like if we get models like if we get accuracy of 75%, say on gender, and we get a very less accuracy like 40% on age. So we want to improve both the accuracies. Like a model with 70% gender accuracy and 60% age accuracy is better than getting a 80% accuracy on gender and just 30 or 40% on age. So we want to take both the accuracies to same level and make the model learn age and gender simultaneously. And that inspired us to use the collaborative learning rather than the standard trivial approach.
Okay, now I got it. Okay.
Yes.
Uh, can you go to your this the whole architecture? You have one image, no, the flowchart.
Sir, of the full pipeline, right? In the
Yeah,
starting.
yeah.
Okay, sir.
So you are having the video and you are extracting out the frames. Then you are using faster RCNN for bounding box recognition. From that, you would be having the body images. Then you are using OpenCV Cafe model for extracting the face, and then you are using ESR GAN. This is super resolution GAN, real super resolution GAN, to extract and to increase the resolution of the image. Then you are okay for face. You are using on the face images you are using for age, and the body images you are using for gender, right?
No, sir. I would like to elaborate on that. We are using the face images and the body images simultaneously. We are
Yes.
predicting, we are extracting the features from the M3 model for the face, and then simultaneously predicting the features for the body images. Basically, both the models are similar architecture, but they are trained on different data sets. Like for the face one, it is trained on UTK data set so that it has the capability to learn the parameters, learn the features of the face. And similarly, the M3 model used for body images is trained on the PETA dataset, which is a full body dataset. So basically, the architecture is the same, but that they are trained on different datasets so that we could extract the features of both faces and body and then concatenate them through a concatenation layer and then apply the concept of collaborative learning for our spatial weighted loss function.
Okay, for age classification and gender classification, you are using two different networks, right?
Yes, sir.
Yes, yes.
And the age classification, is it, I mean, are you predicting the age range, or you are using the regressor, or you founding the number only?
Sir, we are using classifier, and this was also because of the data set that we received. Actually, we are using the better data set and we are using the classification layer.
Okay. So what I mean to ask you is, in the age classification layer, the output is the age range, right?
Yes, sir. It's a age range, but basically we got why we are using range. We have a reason for that because you are using a PETA data set, which basically provides the labels as the range, like 0 to 10, 0 to
Okay.
15, then
Yeah,
15 to
this
30.
is what I was. Yeah, yeah.
Yes.
Q&A time is over, like we have exceeded it. So we have
And
to move to the next team
one
now.
last question. One last question. How much time
Fine.
is it taking for the inference for a video?
Sir, we have not rigorously tested on the whole pipeline, but as we have tested on a video input of 30 seconds, we think that the inference time would be 10 seconds or 15 seconds because of mismatching pipeline. Like we are training, basically it's taking the inputs and then rendering it, but we could make it faster. And that's what we could work on.
Okay.
Yes, sir.
Yeah. Anything else from your side, Vinod?
One question. So here we have separate classification layer for age and gender, right? So the input image, so the body features and the face features both are concatenated and provided to both separate neural networks, or how is it? It's provided individually, like body is provided to one thing, and how is it?
So for gender classification and age classification, we are using a set of linear layers or fully connected layers. So the concatenation.
That's okay. That's okay. Here the features you are using, you have the face feature and the body feature, right? So both are you are using for age and gender, or
Yes, sir. We are using both. The final concatenated layer is like concatenation of face features and body features, and we are using that for age classification as well as for gender classification.
okay? Okay, so here I have one question like, so what do you expect? What kind of features from the body can extract for the age and gender prediction? Yeah, because the facial I can understand. So yeah, the doubt is like what kind of features it will be extracted for the classification.
Sir, I would like to answer it very naively. Like for the body, we can see the clothing sense and the size of the image and the dimension of the body. But if we only see the body, we would see the clothing and the bent body, or is it person standing position? But we would completely or ignore the face. Like basically, face is very small part of the body. So
Okay.
we would like to extract the features of face separately in another model which is specially trained on the face images. So it is highly trained to extract the face features like your spectacles, like your color of the hair, like color of like wrinkles. I know that wrinkles would not be visible, like beard. It is specially trained on that. So basically
Okay.
both the models are trained on their specific task, and then we are concatenating the features. So I think through the collaborative learning we could increase the accuracy to a greater extent. So that was
Okay.
our motive. Yes.
Yeah. Okay. Thank you.
Thank you, sir.
Okay, so now move on to the next team. That is team number 4. You can raise your hand. Uh, I guess all the members from team 4 is there on the stage. Okay, you can start.
I think you're on mute, Anas.
Yes, you're not audible.
Yeah, we are starting now. Hope I'm audible. Hope I'm audible, right?
Yeah, you're audible.
All right, cool. All right. Greetings to everyone from Team 4. We are here to present our solution to the age and gender detection problem. Next slide, please. So the primary challenge we aim to solve is to accurately predict the age and gender of people in video footage. Since the pipeline is applied on videos, speed must also be taken into account so that it is more practical and deployable. Also, CCTV footage often suffer from a lot of noise and low resolution. So to efficiently use the information, there is a need of super resolution as a pre-processing step. To calculate the prediction, we must also be able to detect the body for all angles and with high confidence and speed. Finally, for better age and gender prediction, extra signals could be used to supplement the learning. Next slide, please. So we tackle the aforementioned challenges with the following pipeline. It consists of pedestrian or body detection with the use of faster RCNN, followed by super resolution on the cropped image using ESPCN. And finally, we input this into the age and gender prediction model, which leverages multi-attribute prediction.
Am I audible now? Hello.
Yes, yes, you're audible.
For detection of the bounding boxes of pedestrian, we chose faster RCNN with ResNet 50 as a feature extractor. The mean average precision to GPU time ratio of faster RCNN is relatively higher compared to other object detection algorithms. So it is able to make faster predictions while not compromising on the accuracy of the bounding box predictions. We trained this model for 12 epochs on the wider person dataset consisting of 9,000 images with an annotation of bounding boxes for prediction detection in all angles. All the bounding boxes which have a confidence score of greater than 0.6 were selected. Fast RCNN uses an algorithm called selective search for proposal of regions, which takes a longer time. But the architecture of fast RCNN can be divided into two parts. The first part of fast RCNN, which is the novelty in its architecture. It is the region proposal network. This outputs feature vectors of anchor boxes, which are selected as foreground, which has high probability of having an object in that region, making this model 10 times faster than fast RCNN. Then in our case, we implemented this RBN via CNN feature extractor ResNet 50. The second part is a regressor and a classifier where the regressor outputs a refined bounding box for each selected anchor box, which is selected as foreground, and classifier detects the object. Thereby, we get the bounding boxes for prediction of the pedestrian detection.
Okay, so after we get the bounding boxes for the people, then we pass them through the supergan, as was hinted in the problem statement. We don't pass the entire image through the supergan because we need to save the time. So we only pass the bounding boxes which we find. And the reason we chose the supergan as ESPCN, efficient subpixel convolutional neural network. Reason we chose this is primarily on the basis of its speed, and the reason this is faster than other models is because like most models first scale up the image from lower resolution to higher resolution using bicubic interpolations, and then they pass this higher resolution image through the entire model. So this takes a lot of time, and bicubic interpolations don't add any additional information, so that's slightly waste of time. So ESPCN, on the other hand, only switches to high resolution at the very last layer, and all the features are extracted in the lower resolution itself first. So that definitely improves the speed. And on benchmarked on the set 14 data set, it takes 4.7 milliseconds to process a particular image on average if you use a K2 GPU. So here we have a photo of the original image of a pedestrian, and then there is a 3x interpolated image and compared with the ESPCN super resolution image. So again, as you can see, the uh, ESPCN only upscales in the final layer to save time, and like the paper reports considerable improvements compared to the other models like SRCNN, like the accuracy PSNR scores it has of 29.42 and time 0.25 seconds compared to SRCNN, which has 29.14 PSNR score after taking 2.5 seconds. So it's better in both accuracy and time. Yeah. So now we'll go into the prediction model.
Next slide, please. So we use the PETA and the PA100K dataset to train and validate our age and gender prediction. PETA contains around 19,000 images, annotated images across 35 binary attributes, whereas PA100K contains about 1 lakh images on 26 binary attributes. These attributes cover information ranging from attire to accessories and even include the predicted age and gender. Next slide, please. So we use ResNet 50 with its pre-trained weights as the backbone for our model. It is made up of bottleneck layers, which consist of alternating CNN and pooling layers, followed by a fully connected layer. As we earlier did with faster RCNN, we chose to use ResNet 50 for its high speed to accuracy ratio. It has one of the highest accuracy densities, which is calculated as the ratio of accuracy and the number of parameters. So it is essentially a measure of how effectively the parameters contribute to the overall prediction. And ResNet 50 is also rated as the best by Stanford's Dawn benchmark for end-to-end deep learning training and inference. It has the lowest training and inference time to achieve an accuracy of 93% on the ImageNet classification task compared to its counterparts. Then next slide, please. So coming to the actual model architecture. So human intuition often relies on factors such as attire, hairstyle, accessories for estimating age and gender for a person. For example, a person with a long hair and skirt is likely to be a female, or a young school student is likely seen carrying a backpack. So we hypothesize that these signals could even aid the neural network as well to predict age and gender better. It has been shown by earlier works that much like human eye, computers also pay attention to certain sections of images to detect a particular feature. We designed our model architecture to parallel the human process by first predicting the 35 attributes of the PETA dataset as a binary classification task. Then using that, we predict the 4 age ranges and one gender attribute. To generate the embeddings for these input images, we use ResNet 50 as detailed before, which outputs a 2048 size vector, which is then fed into a linear layer of output dimension 35, corresponding to each of the attribute. And then the logits of this layer is passed to another linear layer of final output dimension 5, and finally a sigma layer for calculating the probabilities for these age and gender categories. So to train our model, to make use of the attributes, we leverage transfer learning to first learn to predict the various attributes mentioned above, and then further fine tune to predict the age and gender by adding an extra linear layer. So specifically, we use the PETA dataset with a 70-30 split to learn the 35 attributes for 20 epochs. Later, using the same split, we fine tune to predict the 5 age and gender categories for 5 epochs. To make our model a dataset invariant, we also further fine-tuned it on 100K 10K instances of PA 100K dataset for 5 epochs. So during our entire training process, we make use of data augmentation such as resize, horizontal flip, affine, and color jitter to build a more rigid model. Next slide. So outlined here are the F1 score for each of the attribute, along with the age and gender categories. Although the attribute prediction score varied, the age and gender predictions are seen to have consistently high F1 scores. The graph on the right shows the F1 score on each of the category of age and gender, with and without the help of other attributes. From the side-by-side comparison, it is evident that using extra attributes, extra features had a consistent increase on the F1 score across all the concerned categories. To be precise, the average increase in the F1 score is around 0.0868, which is on average 11.6 increase across all the categories. Next slide. So finally here, we present the category-wise F1 and mean accuracy score for each of the age and gender categories. We achieve a mean F1 score of 0.854 for the 4 age categories, and with an overall mean of overall mean F1 score being 0.87. The MA score also follows a similar trend, and the mean MA score across all the 5 categories is a whopping 0.896. So thus our model was able to predict the age and gender of people fairly well, which we set out to achieve. And that's pretty much it. Here are our references, and next slide. Yeah, that's pretty much all. Any questions?
Okay, so now we can move on to the Q&A session.
Rishikesh? Yeah.
Yeah, go,
Go ahead, Pratik.
No, I was just asking what is the latency you have recorded Team 4?
So the inference time?
Yes.
So it was around 1 second for per frame on GPU, around 2 or 3 seconds per frame on CPU.
CPU, right? Okay,
Yes,
and for a video of 30 seconds, right? Okay, if I consider as for example 30 FPS image, right? Hello. Yeah, 30
Yes, sir.
FPS image. So how much if I consider it a 1 second, then 900 seconds, right? For 30
yes,
seconds
sir.
video, 15 minutes. Hello?
Yes, sir. Yeah, that will be accurate. So for around on our testing for around 700 frames, the calculation was made according to that. So for a 30-second video, it will almost be the same as well. This ratio should follow on GPU. So the GPU we used was on the standard Google Colab GPU, but it depends. It could depend on GPU to GPU.
Okay. Yeah, Vinod, you were asking something.
Rishikesh, so you were using faster CNN to detect complete body, a person, or only face?
Yes, sir. Body, as mentioned before, it was only on the body to detect the body images. So we trained it on the wider person data set to detect only the pedestrian, so just the body detection.
Okay, so then how do you extract the face?
Sir, we are actually initially when our model was a combination of face and body, but later we realized that face could not be detected for all the possible angles. So it might actually do more harm than good for our model. So our model is purely based on the body to identify all the different attributes, and then use those attributes like how humans do to predict the final age and gender as well. So I think from earlier studies, also from what we read, was that most of the time for age and gender, like it actually uses the face by in itself. So it pays attention to the face to predict age and gender. If we go to the model slide, Ayush, Anay, there is a picture where it shows for each of the categories what it pays attention to. So by innately, it is actually paying attention to the face, but we are providing more information on the about the attributes like what they're wearing, and hairstyle, things like that, accessories, to help it guide further with age and gender prediction.
Okay, so basically you're using complete body. Okay.
Yes, sir. Yeah.
Okay. Then can you move on to the ResNet model? The ResNet
Sorry,
tool.
sir.
Can you move on to the ResNet page?
ResNet page. Before. Yes.
Okay. No, the architecture one. I think just before this one.
So the entire inference pipeline you're saying, or this?
Yeah, this one. Yeah, this is sufficient. Okay. So here you are using single neural network, or how is it for both the age and gender?
So the final layers you're talking about, right, sir?
Yeah, final layer, or okay, the neural network.
So actually, yeah, sir. So initially we fine-tuned it on a single linear layer, output layer. So from the embeddings of ResNet, we have a single linear output layer, and then we added an extra linear layer to make use of the fine-tuned attribute prediction. We use that prediction to guide us with the age and gender prediction by adding a linear layer of output size 5. So yeah, so in total there will be two subsequent linear layers with a sigmoid layer.
Okay, so basically your input will be okay. So you have one neural network, and in that one you will be having the two fully connected layers at the end. So one for each and one for other, or in one fully connected layers you have both.
So in one fully connected layer, the first fully connected layer is primarily fine-tuned to predict the attributes properly, and then the subsequent the fully connected layer is fine-tuned to predict the age and gender. So it is using the previous fully connected layer to help it predict better.
No, here my doubt is like you are using one neural network for both age and gender, or you are using two neural networks?
Yes, just one neural network, sir.
One. So in one neural network, how you are mentioning your classes, like, so okay, see, age and gender, that's a different category, and age is different category, gender is different category, right? So
yes,
how
so
your input is like?
So we're formulating this as a binary classification task where the first classification, category would be an age range. The first 4 are age ranges, and then the last one is the gender category. So it is primarily a binary classification, multi category
multi-label?
Multi-label prediction. No, sir. It is a binary. It is binary only, sir. So, but we have 4 categories for each of the categories.
Okay, for gender you have 4 category. Sorry, for age. Okay, for
yes.
gender you have 2 category. So your input labels
one category with
contain both. Okay, your input label will contain both the age and gender, or that's I'm not clear. See, for example, in an image. So, okay, in this itself, you consider this 256, 129, 3, right? So, in this scene, a person is there. So, how you will label him? Okay, so you will
excuse me, can I answer this?
32, some 35. Okay. So then output you will be having two networks or network. I'm not clear this one.
What can you once more, please?
Hello, Pratik.
First, I
Hello,
think,
hello. Am I audible?
yeah, Vinod, your voice is breaking actually. Uh, okay, I think what Vinod meant to ask is, first of all, what is the label you are giving the input? So, for
Okay, so
example, you are having,
hello.
hello, yeah.
Hello, yeah, we are treating the 5 labels separately. Like we say the age category less than 30, 30 to 45, 45 to 60, and 60 plus. All of these are like independent of each other. We are treating them as like each of them will have the probability of them being true, irrespective of the other labels. Like we are using sigmoid function, so the probabilities here don't add up to one necessarily. And so yeah, and then the fifth class is gender. So we noticed that when we ran some of the T100K as test for testing, we noticed that the age categories also don't necessarily correlate much. Like sometimes you might have 30 to 45 having a high probability, and 45 to 60 having a and 60 plus having a high probability, without the middle 45 to 60 having a high category. So then we noticed that we might benefit by keeping all four as separate categories, independent of each other.
Vinod, are you clear on that? You're on mute if you're saying something.
Okay. Oh, sorry, I could not hear properly. Okay, so my doubt was like, okay, in softmax for age, okay, you have 4 categories, okay, so you will be having 4
Yeah, we are
regions
not
in
using
there.
softmax. Like I
The,
said, each of the age categories are being treated
You are using
independently. Like
sigmoid.
yeah,
yeah, we have
and
not
like
used
I
Okay.
explained, like in P100K data set, we observed that sometimes in our tests, the like 30 to 45 will have a high probability, and 60 plus will also have a high probability, but the middle one probability will be less. So like there were instances like that, and then if we do some average or something like that later, I mean it was messing up with the results. So what we did was we took them as independent classes, and we just predict the probability of each class separately. Like these are 5 independent probabilities, they don't add up to one.
Yes,
Okay.
there are 5
Okay.
labels in our
Okay.
classes.
And what if the two probabilities are equal? Like for this for two age ranges, like 15 to 30 and 30 to 45. Let's say these two ranges are there, and suppose the sigmoid gives you the same number for these two classes. Then what? How you would handle it?
Yeah, so this was one disadvantage of the way we chose. Like I said, first we had tried doing like we were taking the average, or if like multiple are there, then we were doing the weighted median. Like after there are if there are 4 classes and you have the ranges of all, and if you have the probabilities of all, then we were taking the median along with paying attention to the weights. But we noticed that there was an issue there. Like I explained, if the first and the last category has higher probability, then the answer will be predicted for the middle one, although it has the very less probability. So so that's why we switched to the giving only focus to the highest probability among the ages. Among the four age categories, we only use the highest probability one. But yeah, this also has a disadvantage. If the results are 0.5, 0.5, then yeah, if they are very close, then it won't predict very well, I guess.
So okay, correct me if I'm wrong. So the reason why of keeping the single neural network for age and gender is because of the fact that you thought that there is a correlation between whatever features have you used for gender prediction. Those same features could have been used for the age prediction also, right?
Yes.
Okay. Okay. All right. And have you tried using two neural networks separately? I mean, just asking, have you tried it?
Sir, so our entire model's focus was to actually kind of learn the interdependence between the different attributes. We thought that this actually might be a better way. This is how it was, the baselines were even being implemented. They were using a single layer to classify all the attributes. So we are using this pretty much the same idea. We're building on that by using multiple attributes to specifically fine tune it on age and gender.
Okay. So reason why I was asking you, I mean, for that, because it looks interesting, this architecture. Yeah, and but for example, as I mentioned, no, if the two age ranges have same probability, then the
Yeah,
network
we
would
Sir,
have
have
confused.
one disadvantage there. But when we
Yeah,
tried, was the data set on which we trained, there the probability for two different age ranges was not high. But when we were testing, we found that suppose for one kid, the 0 to 30 age was also high probability and 60 plus was also high. Then if we use this, I mean, this Bayesian approach, then that would have been in between, and that would
mm-hmm.
have caused a lot of error. So we chose to be deterministic in our approach, and also if suppose there are two classes having high probability, there we are at disadvantage, but there for predicting the exact age, it takes the mean of both of the ranges. Am I audible?
Yeah, I lost you in between, but it's okay. I understood. Yeah. Anything else from your side, Vinod? I'm done from my side.
No, I mean
Okay,
for this
so we
probability.
can move on to the next team. Team number 6, you can raise your hand.
Thank you, Team 4.
I guess everyone is there on the stage from team 6. Okay, team 6, you can start now.
Hello, am
You're
I
not,
audible?
yeah, you are audible.
Like I think my teammate is facing some audio issues. Like just give me a second.
Ask him to rejoin.
Rishita, if they're asking, if they are facing some issues, maybe other team can.
Yes, yeah,
Like just
so you can
give us a second. Yeah.
we can ask the next team and you can perform after that if you want. If you want some time to sort it out.
Just give us one more second.
Okay, fine. Okay, fine.
Give my friend access. Like he rejoined. Aryan Pandey T6.
Ask him to raise his hand. What is his name?
Raise your hand, Aryan Pandey.
Okay, okay, fine. I guess now, Aryan, you're not audible still. Aryan, can, I guess I have given you the
Yeah, we
access,
are ready.
but I'm
We are ready.
okay,
Hello,
fine. You can
am
start
I
the
audible?
session. Yeah, you are audible.
Yeah, okay, I'll just speak through my teammate. My teammate is Shekhar. Okay,
You
right.
can,
Just let me know if you can see us.
yeah, your screen is open. Okay, so you can start now.
All right. Okay, sorry for that delay. My system was not
Yeah, no problem.
all right. Okay. So good afternoon, everyone. We are Team 6. We will be presenting our solution for Bosch's age and gender detection mid-prep problem statement. So to give you a slight idea about our presentation, we will first be giving you the pipeline overview, followed by the data set which we created. And we will be telling you about a few details of the pre-processing pipeline, the models that we used, and all the alternate approaches we tried, because we tried quite a good number of them. Apart from that, we will also be giving you a slight idea about what we think could be done as the further scope for this whole project, because this is indeed something that looks like a long-term project. And all the improvements that we made since the code submission, since we were kind of interested in working on this even after the deadline was done. So to give you an idea of the pipeline, we take in an input frame from a video and we perform exposure detection or illumination detection to get an idea of how lit the image is. If there is very low light or very high light, any facial features could either not be visible or be over visible, which could create problems in the age or gender detection. So for low light correction, we have a low light image enhancement system, and for overexposure, we apply clarity. So after we have the corrected image, we pass it through a face detection system, which creates bounding boxes and segments out these images, it segments out these faces from the image. Now, since most CCTV cameras are also really low resolution, we perform face enhancement on these images. After we perform face enhancement, we have the final faces which we would want to pass through our gender and age model. So the final output for this input frame would be something like this, where you can see the bounding box created on these two people along with the age and gender represented on the two faces. Over to Neham, who will be talking about our data set.
So we created our own dataset because datasets such as PETA and UTK aren't available for commercial purposes. So to comply with the BOSCH regulations, we scraped our own dataset consisting of around 8,000 images, which are all available for commercial use. So like after scraping the images, like we pass it through a state-of-the-art face detection module to extract the faces from the images. Like doing so, we get around 6,500 faces. And like we use a deep expectation algorithm to label the age and gender for these images. But like we manually correct all the images where the algorithm is misclassifying the particular face. So we manually annotate like the misclassification cases. So here are some statistics for our dataset. So like the range of the age range of our dataset is from 2 year old to 88-year-old. It covers a huge variety. Yeah, next slide, please. So here are some samples from our dataset. Like as you guys can see, like it shows a considerable variation in the race, ethnicity. So it can generalize well to different faces, and like it won't face any issues regarding that. Over to Shekhar.
Yeah, so to extract better feature from an image, the process is according to its brightness exposure level. For this purpose, we use illumination detection technique. Here we first convert RGB image to lab color space to measure brightness of image. L channel is for luminance and A and B are color dimensions. Based on this, we classify images as overexposed, balanced and underexposed. For underexposed images, we apply low light enhancement through 0 DC. This method is inspired by curve estimation techniques in image processing and it is applied for 8 iterations as mentioned in research paper for best results. Over to my fellow presenters.
So for a face detection algorithm, we use dual shot face detector, which is a CVPR 2019 paper. Like it specializes for detecting faces, and like it has three novel contributions that addresses like three key aspects of face detection: better feature mapping, improved anchor-based data augmentation, and progressive loss design. So it's able to detect faces over robust different real-life scenarios, and it has specialized loss functions for faces in crowds. Uh, Next slide.
Yeah, so after we get the cropped face from the face detection model, we perform face super resolution since we want to extract the features from the face to perform age and gender detection. So usually for super resolution, instead of in just going for super resolution, we looked at some face restoration methods. So GFP GAN, also called generative facial prior GAN, not only it reconstructs the facial features and not only performs super resolution but also performs color enhancement. So how GFP GAN works is that it generates a facial prior, and this facial prior is then used to provide this super resolution, and it provides a good balance of realness and fidelity, and it actually reduces the number of artifacts. So what the GFP GAN has is a degradation removal module, which is then passed through a pre-trained style GAN, which generates the facial image we want. So why we took GFP GAN over something else like ESR GAN is because it involves training losses that take into account like facial component loss that basically that enhance facial features like the eye, the mouth, and identity preserving loss, such that it basically ensures that the restored result has the smallest distance from the ground truth face feature embedding. So this is why we used GFP GAN to perform super resolution and color enhancement.
So for gender detection, we use Net V2. So Efficient Net V2 is a family of convolutional models that have very high parameter efficiency and good transfer characteristics. So it is pre-trained on the ImageNet 21K dataset, which contains around 14 million images. We then fine-tune this model on our script dataset, and we achieve a accuracy of around 94.38% on our validation dataset.
So for age regression, we use DLA34. DLA34 is an architecture that aggregates all the hierarchical features in an image. This is especially useful because many times high-level features are very useful in predicting the actual age. We predict the actual age instead of bins because we feel that that would be a better estimate of the age of a person in a video. The RMSE which we obtain by using the DLA34 architecture is 7.21 on the age scale of 2 to 88. So as for the alternate approaches that we tried, we also tried retina face for the face extraction. We ended up not using this because it has a very high inference time and we want our solution to be able to work in real time. We also use GPen for face super resolution, but once again, this was not able to reconstruct the facial features completely, mostly because it wasn't trained on a data set which had a large age range. So for older people, it was not able to reconstruct features like wrinkles, or for younger people, probably something like like baby hair, stuff like that. And we also had a custom model which we made for age regression, which almost gives us the same metrics as DLA, but DLA outperforms this. So the custom model which we had was a common feature extractor and for some number of blocks, a male feature extractor, which so the input for this is the image and the gender. We have a common feature extractor which extracts high-level features, And then we have a male and female feature extractor, which extracts features depending on the gender of the person. As for the experiments, you can see that the difference between the DLA34 that we use and the DLA34 in the paper is that in these base convolutions, we use double the number of filters that the people use in the paper. So that gives us a slightly better representation of all the images in the data set.
So if you look at further scope that we looked at for the project is, one could be that since we usually have multiple CCTV cameras in places like shops, we could incorporate multiple views of the same person for better facial feature extraction and prediction of age and gender detection. Apart from that, since we had to create our own commercially data set from commercial images, if we had more time, we could have scraped more images and manually annotate them to get better results from our models. Apart from that, another thing that we would like to try is creating a single network which has multiple heads for age and gender prediction, because we are under the hypothesis that the same facial features that are extracted from the network can be used for both age and gender prediction. Apart from that, we thought we could use the models on training on the full body instead of just faces. But for that, we again would read a commercial data set, and scraping that, we will be able to maybe implement this as well. So the improvements we made since our code submission, since we were very interested to work on it as well, was first thing was we implemented batch processing so that I'll be finishing it. A batch processing so that we could decrease the time for inference by parallelizing the computation. Another thing we did was we pruned the model using the lottery ticket hypothesis, where there's the subnetwork that can be obtained by pruning the network, which trained in isolation could also reach the similar accuracy to the original network. So that is something we performed to decrease the inference time. Apart from that, we implemented face tracking using the SORT algorithm, which is the simple online real-time tracking, and annotated that on the input video so that we could provide the annotations for the age and gender. Thank you so much, and we are very sorry for the delay in the beginning.
We are open to taking any questions, and if you want, I think we'll also have an output video generated, which we could.
Yeah, we have a yeah.
But yeah, we're open to any questions that you guys have.
Okay, we can have now Q&A session.
Hi, Team 6. Okay. So one thing one question that I'm going to be asking from with every team is what is the time that you have recorded for each frame, inference in each frame, and for the 30-second video?
Okay, so the video samples that were sent over to us by you were of 6 FPS, and our whole pipeline can run in real time for processing that 6 FPS. So we're processing close to 6 frames per second through this pipeline.
Okay, so what is the for how many seconds you have recorded for the inference for a single frame?
For a single frame, it will be 1/6, somewhere close to that. For a single frame, it should take about 1/6 seconds. It's 6 frames per second on an average.
1/6 seconds, right?
Yeah.
Okay.
If there are any other questions that you guys have, or you want me to move over to some other slide, please do let me know.
Can you go to the next slide? Next. Okay, so you have Niham was saying that you have manually annotated that data, right? You have scrapped it.
No. So we pass it through a deep expectation algorithm, which gives the labels for age and gender, but we manually see if the labels are correct or not. So it's not like we are manually annotating. We are checking the annotations against the image, and we are correcting if the images, like if the annotations are wrong.
Next slide. Next slide. Okay, so this RGB to LAB conversion, you are doing it in the beginning only for this illumination detection, right?
Yeah, we are
Or
just this is just for illumination detection.
just for illumination detection, or
Yeah.
and while in the like in the classifiers, you are giving the RGB images only, right?
RGB. Yes.
Yeah, RGB images.
Okay. Next slide. Okay, so this is where you are using the LAB, right?
Yeah, so the LAB, okay, so the LAB which we are using is on the original image. So you can see over here on the left hand side, we are using the LAB conversion on this image. If
Illumination
the image,
detection, and you are correcting.
yeah, we are correcting. That was a correcting step which uses a proper 0 DC model, which is currently the state of the art for the low light enhancement.
Yeah, like so for the luminance channel, we compute the average luminance for the image. Like we take a average over we take an average over the height and the width, and on the basis of that, like we do some thresholding, whether it's low. Yeah.
Okay, got it. Okay. Move further. Yeah. Okay, so this is DFSD. Okay, I have not worked on it. So how is it different from okay? How is it different from other state-of-the-art classifiers? Sorry, detectors.
So it has a novel bounding box regression loss, which is specifically designed for crowd scenes, which is called repulsion loss. So the repulsion loss is driven by like two motivations, like attraction by the target and the repulsion by other surrounding objects. So let's say like if there are two faces which are very close to each other, like which can be there in a concert or something like that. So the repulsion term prevents the proposal from shifting to surrounding objects. So there's a region proposal network which is there in like faster RCNN and those type of algorithm. So the repulsion term prevents the proposal from shifting to surrounding objects, and the like it's more crowd robust localization. So
Okay,
like
and
it outperforms.
okay, so
Sorry.
DFSD for face detection only, right?
Yeah, DSFD. Yeah, it's for face detection.
Okay. So what I'm asking you is, you can manually train. You can train it on custom data also, right?
Yes, it's possible to train it on custom data.
Okay. So it is having a faster inference time. Okay, and go ahead. Next slide. Okay, so this is you are using GFP GAN here for color stabilization, for increasing color stabilization as well as super resolution, right?
Right.
Okay.
Yes.
Yeah, I think okay. I think it is clear from my side. Everything is clear. So actually, Vinod, he messaged me just now. His internet got disconnected, and yeah. So I have noted all the points, and thank you, Team 6.
Thank you.
Thank you so much.
Yeah, thank you so much. Thank you so much.
Thank you, Team 6. Now we can move on to the next team. That is team number 18. You can raise your hand. I guess everyone is there on the stage. Yeah, you can start your presentation. Team 18.
Yeah, I'm presenting. Can you see my screen?
Yeah, your screen is visible.
Yeah. So
Yeah, give me a moment. Sorry for interrupting. Vinod, are you here? Is your
Yes,
internet
Pratik,
being
now,
clear?
yeah, now I'm
Okay.
available.
Okay. Sorry. You go ahead, teammate.
No problem. Utkarsh, please go ahead.
yeah. So good afternoon to everyone present here. So we are team 18 and we are going to present our solution for BOSCH age and gender detection challenge. Next slide, please. So the basic problem we are trying to solve is gender and age prediction in CCTV footage. So a lot of research has already been done on gender and age prediction, and the existing models can provide state-of-the-art results. But what distinguishes this challenge from the rest of the general age detection challenges that in CCTV footage, most of the images that we get are of low resolution, and also the person may not be always looking in the camera, may not be facing towards the camera. So we picked one of the pre-trained model, and so let me first give you a brief overview of what the whole architecture of this pre-trained model was, and then we'll go into what improvements did we do to this existing architecture. So our pre-trained model uses retina face and arc face to detect faces in the images, and then it provides an embeddings for each of the faces that are detected. And then those embeddings are passed into a multi-layer perceptron network, which has like all the things like skip connections, batch normalizations, and all that stuff. So it's a big architecture of fully connected layers to do the gender and age classification. So at the end of the fully connected layers, we have two branches, one for gender and one for age. Gender is a two-way classification, male and female, and age is a 101-way softmax classifier. So we assume that our ages is going to be between 0 to 100. And instead of posing it as a regression problem, which is like difficult in the case of to optimize in the case of age, because like we don't know the exact age, and same person can we can think of in multiple age groups. So that's why we pose it as a that architecture poses it as a classifier problem. Next slide, please. Yeah, so this is a brief architecture. Like we use a face detector and pass it through the network to get the age and gender predictions. Next slide, please. Yeah, so if we use this architecture as it is to predict the age and the gender in the CCTV footage, this may not work always. So we have a classic example here where it's a good high resolution image where people are also like for humans we can clearly see the people and guess the age and the gender. But if we pass through this network, it will fail. So a few of the issues we can see here already are that the people here are not facing towards the camera, the first thing, and the second thing is the people are far away from the camera. That's why the size of the faces of the people are small. Our pre-trained network was trained on IMDb wiki dataset, so which is basically images of celebrities scraped from internet, and and that dataset has the faces of the people are almost like centered focus images are there. So that's why our network has a hard time detecting these people in this CCTV footage. So there are two things we can do to improve our accuracy here. One is use super resolution to increase the size. So since each person's face is small, so maybe we can use super resolution to increase the resolution of the image and then pass through it. And the second thing is to use a person detector. So first we detect a person in this image, crop the whole body of the person, and then pass it through the our original pipeline. So next slide, please. So first, let's discuss how person detector improves the results. So let's say this is the same image of a girl from the last slide's image. So we can see earlier the network wasn't able to predict the age of this girl. So, but after using a crop of this person, we are able to do so. So, so we are using a pre-trained YOLO-based person detector. So we used YOLO in YOLO-based person detector because YOLO has like faster inference time and is more real time than other of its counterparts like RCNN and fast RCNN. Next slide, please. So yeah, this is again an example of where the person detector is able to detect the age. Next slide. Yeah. So our architecture after just this step is like we are keeping the age and gender classification architecture same, but we are instead of passing the image or the frame directly to the face detector, we are passing it through a person detector and getting the crops, and then using those crops to pass it to the face detector. Now my friend Akhilesh would explain how we can use super resolution to improve our accuracy of the model.
Okay, so before going over that, so generally, as my friend Utkarsh said, that many of the CCTV footages are low resolution in nature, but the new CCTV are coming with coming with better resolution, and also the sample data set that is being shared over the Slack is also being considered to be a 720 pixel video of varied length, I guess 2.5 minutes and 30 seconds. So yeah, so the architecture overview for the current architecture for low level CCTV footage was to extract to take a person detector, apply it on an image, then do a super resolution on the crop, and then finally use the face detector to predict the age and the gender with the face. But Chanvi, next slide. Actually, we experimented with several super resolution model to enhance the segment of the image we captured using person detector, but ESR again seemed to give a good results. We actually experimented using the super resolution model before the person detector, so that it will be our general intuition was that it will be able to capture more person in the image, but that didn't happen. Also, the time taken by the super resolution to work on the whole image was much more greater than the to work on the segments of the image, because there is too much background in the CCTV that is not moving, and we can say that 50 to 60% of any image is background. So the time taken for super resolution to process on that image was big. We That's why we moved to super resolution to the second step, that is after the person detector. I don't think so, buzzer. I guess we just started. We have been only 6 minutes. Using means okay. I will go on. Using super resolution was Janvi. Yeah. So we tried some frames from the provided video on the Slacks, and we found that it was taking for 720 or 1080 pixel video. It was taking 30 seconds on Collab GPU. On an average, it was again taking 20 seconds. Means there are many GPU available, V100, P100. So depending on that, on the Collab GPU, if we get a better GPU, it may come down to 20 seconds. But for 720 or 1080 pixel video that has been given, the super resolution was computationally expensive, but without using the super resolution also we were getting a pretty good results. And the decay in the accuracy or the metrics, we didn't see that much without using the super resolution. So we can show that in the next slide, Janvi. Yeah, we can see that these are the two same images. On the right, you can see that without super resolution, it predicts the age as 27 and female as 100%. On the right, if you on the left, if you see that is a super resolved images, means you can compare that by the size of the text. The text size is fixed on the images. So the text size is much smaller in the left side video, and so we can see that the after using that too, the age is nearly same and the female prediction is still 100%. So the super resolution didn't have much to give on 720 or 1080 pixels CCTV footage. Next slides. Yeah, so we tried with image sharpening tools to give from the OpenCV library to sharpening the images to capture the bounding boxes around the person, but that didn't help. We tried OpenCV library, that is a cheap tool to compensate with the super resolution to give a better faces bounding box, but that didn't help. Next slide. We can see that the same kind of result. Janvi, next slide. We can see the next same type of result that in both cases the right side, the bottom right side image is the sharp one and the top left image is not so sharp one, but the results were similar. The change was not big. Next slide. So this was the architecture for this was one of the architecture. The other architecture, person detector, then sharpening, but that also didn't work very well. Next slide. On the on particularly on 720 and 1080 pixel video, but on low level CCTV footage, it was the SuperGAN was working good. On MLP model, we actually for doing the edge regression, we use a 101 class problem. We trained a MLP problem and MLP model on the embeddings that were given by the arc phase and the retina phase, and we then created. We didn't want to make any fixed size bins around the exact edge because the age given by this is in the category 0 to 100 on integer. So we didn't want to create any fixed size bins. So we created because we are treating it as a classification problem, we also have an entropy case. So we are treating whatever the entropy for that current image we have, we are going to give a 10 into entropy on the right side and 10 into entropy on the left side to create that bin for the image. If the more amount of face is visible, the bin will be smaller, and the less amount of face is visible, the bins will be bigger. So that's how we are creating dynamic bins. Next slide. Gender classification was much easier than the age classification. So actually we use a different model on the same kind of image, same kind of embeddings that was much lighter than the age model. Uh, so yeah, so we also trained a MLP, a few layers MLP on the feature extracted from the retina face and R face, and that was giving a pretty good results. Next slide. Yeah, Janvi, hand
Yeah.
it over to you.
To sum up all the experiments and the exploration that we did, the best model that we found is as follows. So from the video, we first get the frames. On the frames, we run a person detector based on YOLO, and then we get a crop of the person from the image. We can have a single crop or multiple crops from a single image. Then the crops goes into the face detection model, retina phase plus arc phase, and finally the features goes into the MLP to regress to predict the age and the gender of a person. So we also tried super resolution and the sharpening of we tried sharpening image to hoping that this will improve the result. But when we experimented, the additional inference time that these techniques added and by the accuracy improvement that we observed was very high. So we decided that we will not include it in the final submission. Yeah. And when we were experimenting all the different models, there are few points that we observed which we think could further improve the performance of the model. So the first one was that commonly the research has been happening on the face detection, and from the face they predict gender of a person. But the problem statement here is little different because we have a CCTV footage in which the faces are not very clearly visible. So we believe that if we train the model on the full body data set, so basically a full body and the label of age and the gender, so it would definitely improve the performance of the model. So this was one thing. And second point is when we were experimenting, we observed that whenever the child's image was present in the video, so it was failing. It was uh, giving the incorrect age a lot of time because we were cropping the face of the child and then feeding it to the MLP. So it was basically not utilizing the height information. So child are generally they shorter than the adults. So this could also be used if we have a full body data set, full body plus age and gender data set. Thank you. We are open to questions now.
Yeah, we can move on to the Q&A session. Judges, you can go for the questions.
So, hello team 18.
Yeah.
Yeah. So, okay. So you have not used the super resolution, right, in the final architecture?
Yeah,
In the final.
the model we submitted, we didn't use the super resolution because I,
It was
I yeah, I remember that it was given that the data set that the Bosch is going to use is going to be a 720 pixel video. That's the high resolution video to work on. On if we use any GAN model that is doing a 2x, 4x, or 8x scaling of the image, then all the things you are going to do after the super resolution will be computationally expensive as much as time that is your scaling. So if the input image is also 1280 into 720 pixels, so it's good enough to go on to do all kind of prediction on that only.
So one question I'm having, suppose you have a video, okay, a person is standing a little far behind the camera, away from the camera, okay, and
Yeah.
okay, she's a lady, okay, and she has a cap, okay, and she has wrinkles over her face, okay.
Okay.
Now, you have extracted out the bounding box from YOLO, and then you have detected her face. Okay, but you cannot see the wrinkles. Okay, because the face that you have
True, true.
detected is of
Means the face is not only 20 to 30% is visible
now.
on that. Only wrinkles are visible, right? On face,
No,
the
wrinkles.
wrinkles.
I'm saying wrinkles are not visible
Okay.
because you have the low resolution image. Wrinkles are
Okay.
not visible. Okay,
Okay. Okay.
not
Okay.
that visible.
Okay.
So, don't you think there would be a need to have a super resolution architecture here?
Okay. So, may yeah, means there is also the needs of super resolution, but if you compare the trade-off between the time it's going to take and the change in your inferences, if the time is not an issue, we can certainly do the super resolution on the person means each segment of the images. But if we are to find a better means low time effective model, then we would be more likely to uh, means ignore the far behind lady.
And yeah, like one more thing I would like to add to your question. Basically, yeah, like computational trade-off is there. Secondly, like if since these are videos of CCTV footages, so most likely the person is likely to maybe come towards the camera in the next frame. So in that frame, certainly the like the object will be the person will be closer to the camera, and in that case we will have
This
like a bigger.
this may not be true always. This
Yeah,
may not be true always. Okay, I mean there are CCTV cameras that are on the roads. Okay, and from you could only see the vehicle coming in the frame and passing out.
Yeah,
Okay.
yeah.
So it may not be the case always. So how much time is it taking per frame for you guys?
on 720 pixel video, the whole model on CPU it's taking around 800 milliseconds for per frame.
For each frame, CPU is taking 800 milliseconds.
Yeah.
And which YOLO version you're using?
I guess 3 or
Euro
4.
V3.
Yeah,
3.
V3.
Okay, YOLO V3. Okay. Uh, And can you go back to this? And yes. And one more thing. Uh, can you go to the slide where your this final classifier is there?
This is the final architecture of the model that we have submitted.
Okay, so the face detector, are you using which network are you using for age prediction or and gender prediction? Are you using this custom MLP or any model like ResNet or Efficient V2 or any model per se?
No.
So
So for
yeah,
sorry.
yeah. So basically, we found a paper. So basically, what they were trying to do is to replace get once they get the embeddings, they had instead of using ResNet or something of that sort, uh, they are trying to use MLP only MLPs to
Yeah,
detect that.
that's what I'm asking. So you have embeddings. How are you getting the embeddings? If you have the face, then how are you getting the embeddings? Have you used any pre-trained model or
Yeah.
for
So
that?
we are using Retina face and Arc face to get the embedding.
To get the embeddings of the face. No?
Yeah.
Okay, and then these embeddings you are okay. I mean, it's kind of like transfer learning. Also, you are training the penultimate layer. Okay, and yeah. So, what is the output of that embedding? How many vectors are there? I mean, what is the vector size? I mean, sorry, what is the vector size?
Yeah. So it's
Dimension?
4096 dimensional.
So just, I mean, actually, so 4096 and in the output of the age prediction, you are having 101 nodes, right?
Yeah.
Okay. So, like if you calculate the number of parameters, then in the final layer, it would be really large, right? I mean,
Yeah.
496 into 101. If you say 4 into 10 to the power 5.
Yeah.
Yeah.
So, uh, yeah, like we can replace this with some like fully like 1x1 convolutions to like reduce the computation cost there. Yeah.
No, I'm saying that okay, this output layer you are having 101 nodes. Is it a good idea to have it? Have you tried any other approach, or how did you come up with the output being 101 nodes?
Yeah, so like our intuition was basically like we wanted to do the exact age prediction rather than doing it in the bins of like let's say 0 to 10, 10 to 20. So that's why 101 was chosen. Like we wanted to predict age from 0 to 100. So that's why 101 way classifier.
Okay. So, any numbers you're having the F1 scores or the accuracies, whatever on the data, whatever you have tried?
Yeah, so the accuracy was around for like 90.66% on there's a data set called ADN's data set, which is one of the like benchmark data sets for age and gender detection.
Okay. So you have used that as the validation or a part of it as a validation.
Yeah.
Okay. Yeah. Vinod, anything from your side?
No questions.
Yeah. Thank you, team 18.
Thank you.
Yeah. Thank you.
Thank you.
Thank you, team. Now we will call the next team. Team number 10. You can raise your hand. And please make sure that you complete the presentation in 10 minutes, otherwise you will be penalized for this. Uh, I guess all the member from team 10. Okay, fine.
Yeah.
Hello, I'm audible.
Yes, you are.
Yeah, I think you can share your screen.
All right. I'll share my screen.
Yeah, you can. No.
Is my screen visible? Shivanshu, could you please confirm if my
No,
screen is
no,
visible?
not yet. No, the screen is not visible yet.
Now?
No.
Okay, 1 second. I'm facing some issues with this. Whew. How come it's not- Um, Shivanshu, could you please share it then? Maybe I'm facing some issues.
Yeah. Just give me a moment. I'll open it then.
1 second. I'll just try it. Oh. Is my screen visible?
Not yet.
Alright.
Can someone else team share?
Yeah, I'll open it and I'll share my screen then. Just give me a moment. I'll share. Is it visible now?
Yeah, it's okay.
Yeah, it's
Okay. I'll. So yeah, I'll start. So good afternoon to the panel and everyone present here. I am Shivanshu Tyagi, and I, along with Prem Bharwani, will be presenting today our solution for Bosch's agent render detection problem. So the initial pipeline that we proposed, like for starting out the solution, we proposed this pipeline. Uh, as you can see, first we are yeah. So the initial pipeline looked like this. The first step was to detect persons from the video. Next, we detect a face in the bounding box obtained and use the super resolution techniques to get the facial features. And simultaneously, we stake the person's bounding box and detect pose. Next, we plan to use CNN models to extract features and then concatenate them to train models to predict age and gender. So this was our initial proposed pipeline that we started out and started testing. So the first step was to detect person. Uh, yeah, and to do that, we used a pre-trained YOLO V5 model. And as you can see, this worked out pretty well on the CCTV footage. So we kept this as a working part. Next, we had the face detection problem. Uh, so we used two approaches to do that, namely Haar cascades and delay. Both of the approaches failed for the dataset that we had, which was very low resolution. Our cascades couldn't capture the variations at this scale. And similarly for DLib, both the approaches that it uses, HOG and CNN, did not work as the resolution was very low and there was very little facial features available to us. Next, we had the super resolution approaches. Uh, we approached this in two senses. First, we use general super resolution models, and the next approach was the face hallucination models. General super resolution models were trained on div2k datasets, like datasets similar to div2k, which were trained on general objects.
And the face hallucination of models tries to regenerate faces from a low resolution to a high resolution, which tries to give high frequency features to our images. As you can see, the results for general GN models are presented here, and the facial features are completely lost while regeneration. And for the case of face hallucination models, we couldn't replicate the results presented in the papers in which these models were presented. So we had to drop this idea. Next up, we had the pose estimation. For this, the open pose key point estimation did not give any result whatsoever on our low resolution dataset or on our low resolution images. So OpenPose also writes that in their documentation that it does not work on low resolution and low contrast images. So we had to drop this as well. Hence, most of the things that we had in our initial pipeline did not work, and we had to move to some other approach. Simultaneously, we were working on the data set. So finding out a data set for this PS was a little bit tricky. So we had to find a CCTV footage data set with annotations of age and gender, which was quite rare to find. We could find these a few data sets for our case, uh, among which RAP is not available publicly. And the other three, which are described here, did not had any annotations for age and gender. So we later on discovered that there is a data set called PA100K, which has gender annotations, but age annotations are not present uh, on for our use case. And that the PETA data set has age classes, which were quite reasonable. So what we did was we used sort of a knowledge transfer from subsets of PETA, which were publicly available, to label PA100K. And the data set that we developed was this one. So the data sets from PETA were used to like transfer knowledge to PA100K. Next, we use this to train a model and then transfer the knowledge to other data sets. So first we pre-train a model on dataset A, and then that outputs a class label. This model is then used to get predictions for the other dataset B. These outputs are then used to get a single age value by doing a weighted sum of model confidence and class average. The datasets label, the final datasets label are produced by taking a random sample from a normal distribution assumed around a value that this model gave, and a standard deviation of 5, which was chosen appropriately by doing some tests. So finally, as you can see, this was the result that we had for the dataset that we labeled. So the gender labels were already present in the P100K, and the age labels that we obtained are quite good for a dataset getting labeled by 2.5K samples to 100K samples. And the final three datasets that we used in our analysis are described here. So we use PETA subsets, PA100K, and Virat ground datasets. The PETA subsets were used essentially to use the labels that it had for age and transfer that to other datasets. And the other two datasets, which are PA100K and Virat ground datasets, are used for testing. PA100K is used for training a custom models, and Virat is a video dataset, which is used for uh, testing a pipeline. And the further descriptions of these datasets are described here. So finally, we had to rebuild our pipeline as most of the components did not work for us. Uh, and Prem will describe it further how we did that.
Okay, good afternoon, panel. So next we move on to how we rebuilt our pipeline using a direct approach now. So the following is a simple and efficient pipeline we experimented with. So now we are directly detecting and tracking people over each frame from the video, and the detections are then passed into a age and gender model, which is then giving a final out. So next slide. So the first segment of our pipeline, which is person detection and tracking, the objective of this step is basically to detect people and assign each of the detections a unique tracking ID, which should ideally remain consistent across frames. So we came across deep sort and byte track models to perform this task. And although both used YOLO for their detection part, the tracking segment was a bit different, which shows up in the results. Next slide. So uh, Following is the comparison. Shivanshu, please play those videos. Yeah. Following is the comparison of the results given by DeepSort and ByteTrack when tested over a sample from Virat ground dataset, which is a CCTV surveillance dataset. As one can clearly see from the difference in the number of tracking IDs assigned, ByteTrack outperformed DeepSort in terms of tracking. So ByteTrack, next slide.
Yeah.
ByteTrack employs a simple yet efficient association algorithm to track the objects. It does so by making use of the byte association method. This takes into consideration even the detections with low confidence scores and then associates them with the high confidence detections from the previous frame. This ensures that it can distinguish between the occlusion and a false positive, such as the background image in the background wall in the image. As you can see in the frames, there is also a background wall that is being detected, which is then discarded. So yeah, I'll just wrap up fast. So ReID also can be achieved by using ByteTrack tracker along with SOTA trackers like DeepSort, which will help us get the ReID. Next slide. So the next part is age and gender detection model. Both of them are custom CNN models that we have implemented. So the following is the age estimation architecture. Next slide. Now we are calculating the exact age. So exact age is being calculated. Basically, the logic that we are using. Let's say we have two people. One of them is a teenager and one of them is in its late 20s. So both of them will lie in the 16 to 30 bracket. So in our case, we found out that we had a normalized data like distribution. So we could use a weighted sum to get the exact age, and that would differentiate the person in his teens and the one in his late 20s. We found that out and we used it this way. And to predict the age min and age max, we used a similar architecture, a similar method. You can have a look at the math that is presented down there. Move ahead. So we had the gender prediction model, again a custom CNN model. The architecture is present here. Next slide. The results for these two models are given here. Both of them had these accuracies in the training and
Hello.
Shivanshu, I think.
Yeah.
Yeah, he's back.
Hello.
I think my network is not there. Hello.
Yeah, Shivanshu, you can continue, I guess.
Yeah. Okay. Okay. Sure. So yeah.
10 minutes is over.
I think due to network there was some issue. I'll finish it in
I'm
5 seconds.
so
Yeah.
sorry.
Is that okay?
Fine. Do it fast.
Yeah. Yeah. Okay. So yeah, these were the final accuracies for the models that were described earlier. So the gender prediction model gave an accuracy of 99.98% on training side, and on the validation side it gave 82.08%, and this was trained for 70 epochs. And similarly for the age detection model, it was giving finally the 95.34% accuracy on training side and 66.31 on validation side, and it was trained for 45 epochs. Finally, this is the output video that is given as the output from our model. And then for the further improvements that we are suggesting another branch in a model where we'll detect a person's height, and we'll use sort of a statistical model which would relate the person's age and the gender to give the height and the gender to give an age, and then we'll ensemble it to give a more accurate age value, as a gender prediction model performs really well as comparison to the age prediction model. Thank you, and we can get some questions.
Yeah, we can move on to Q&A.
So,
Judges, you can ask.
Yeah. So, hello, Team 10. So, can you go to the part where you have explained the annotation of your data? How did you do that?
This one?
The annotation part.
Okay.
Where you have explained. So
Yeah.
okay, I missed that part. So, can you explain again? How did you do that?
Yeah, sure. So the data set A that we are using is the subsets from PETA datasets, which we have trained a pre-trained model on that because PETA has the output of classes of ages. Then those classes are used in a similar way to give an exact age, similar way that we have given it for the final model. That age is then taken as then we sample value from a normal distribution uh, centered around that output value and standard deviation of 5 so that we have some randomness in the label as well.
In
uh,
labeled as.
yeah,
Got it. Got it. Okay, so this is how you have prepared the data. Okay. Okay. Now next slide.
yeah.
Okay, and this is after the augmentation, right? After
The
the
annotation.
annotation.
Yeah.
So the genders were already there.
Yeah, genders were already present in PA100K.
Okay. So you have used the model that has been used the pre-trained model on the PETA dataset, and you have done the analysis, the annotation on this particular dataset.
Yeah,
No?
yeah.
Okay.
Yeah.
Okay. Go ahead. Next slide. Okay. This is okay. Next slide. So person tracking, you have used YOLO for that, no?
Yeah.
Okay.
Sir, for
Can
tracking, we have
you
used ByteTrack. Detection is YOLO. Tracking
come
is
again?
ByteTrack. Am I audible?
Yeah, your voice was breaking in between. Yeah.
Yeah. I'm sorry, sir. We are using ByteTrack for tracking, and YOLO that is using YOLO for detections. So to give a consistent tracking ID, we are using ByteTrack, like it uses the
Okay. Yeah, you explained.
algorithm that I yeah. Yes, sir. So basically, that gives out a good result in this format. So ByteTrack is used for tracking.
Okay,
YOLO,
so deep
anyways,
sort,
is for detection.
so ByteTrack was performing better than deep sort, huh?
Yes, sir. Could you please play these videos? Sir, you can see the number of IDs that Deep Sort assigns. It goes up to 46 or something. And ByteTrack is still consistent with the people, like it is giving up till 7 and sorry, it is going up till 10 IDs, as you can see, and Deep Sort will go up till 40. So
Okay,
like
so it's
it
also
loses
giving
track
the
of people.
overlapping bounding boxes, huh?
Sorry, sir. I
Deep
missed.
sort must be giving overlapping bounding boxes also.
Yeah, actually, Deep Sort misses the point when we have this low confidence scores bounding boxes. So basically, these one work with a minimum threshold, right? And ByteTrack doesn't ignore the ones with lower confidence scores, and it relates the lower ones with the previous frame high detection scores, so that if any occlusion occurs, it ensures that the person is not given a new ID.
Okay. Okay. Next slide, please. Okay, this is here ByteTrack. Okay.
Yeah, this is what I just explained. Like you can see the wall is being discarded because that is a background image and it doesn't have any links in the previous frame. But the second row and the first image, you can see there is a person in red. That person is getting occluded with the woman who is coming ahead, and then it is still detected because in the previous frame we had a high detection score. Like we had 0.8 in the first frame, and then we go to zero point 0.4 and then 0.1 for the red person. That is shown in the first row. So that is not discarded because this algorithm particularly tracks back to the previous frame and correlates them, so associates them, and then doesn't miss it.
Okay. Next slide. Okay, this is the custom. Okay. Okay. Next. So you are not using any super resolution also, right? Because
Yeah.
you already explained they are not working in for
They're not working
Yes,
for
sir.
our data.
We tried it on Virat, and the features are getting worse. So we are getting bad results rather.
And how much time are you recorded for a single frame inference?
Okay.
So it was
yeah.
so it was around 2 FPS for our final pipeline that we submitted. But depending upon the videos and the resolution of those videos, we could get an FPS of around 10.
Also, sir, this is including the video that we are generating. If Shivanshu missed it while I was off, we are giving the CSV format that is there, but we are also giving a video output with the annotations labeled in the video itself. So
So
it is including this.
No, what I'm telling is how much time it is taking for or doing all these things in a single frame.
Yeah,
Yeah,
okay. You mean in
that's
the
what
system?
I'm saying. It's taking on an average around 2 FPS to do all this. But if we
Okay, so
exclude this, we could improve
so
it further.
it's taking 0.5 seconds per frame, right?
Yeah.
Okay. Vinod, any questions from your side?
Can you move to the slide where the complete architecture was there? Prem?
Yeah, Shivanshu is sharing. Shivanshu, could you please go back?
Yeah, here.
Back. The architecture, complete architecture.
Okay, the pipeline.
Even behind.
This
Yeah,
one?
Not this one, the flowchart. Yeah, the pose estimation where this pose estimation part was there also.
Yes, exactly.
Okay, the first one, yeah.
The proposed one, yeah. The one.
Yeah.
Yeah.
This one.
Okay, but you are not no, not this one. Actually, you are not using this post estimation feature extractor for gender, right?
Yeah.
You are using that only for
No,
age.
sir, this pipeline failed. This pipeline
Okay.
failed, as we mentioned. This was the first approach that we went ahead
Okay.
with.
Okay, I saw another pipeline where the post estimation
The
is
last one
used
you
only
mean?
for age.
Yeah, the
Maybe you're
last
talking about the
one
last
is
one.
a bit different.
That
This
is
one.
high. Yeah, I guess you're talking about this.
So you have used this one, right?
No, sir, this
This
is
is the
what we
further.
proposed.
For further improvement.
Further
Yeah.
improvement.
Right. Actually, we tried a little bit of this, but we could not get the height estimation correctly. We found some of the papers, but they were not working pretty well for this.
Okay. Yeah, okay. Yeah, understand.
Like this would help us in
I guess
the discretion when you were talking about with other teams, like when a person is coming from back and someone who is actually small heighted, like a child maybe. So that will improve when we get this implemented. So we expect that this will produce good results.
Rishita, can you add Janani as the presenter?
Yeah, sure. Just give me a minute. Yeah, I've added.
Yeah. Hi, Janani.
Hello.
Hi. Can we move on to the next team? Vinod sir.
Yes.
Janani, do you have any questions?
No, I just joined in. Probably I'll ask from the next presentation.
Oh.
Okay.
Thank
So
you.
thank you.
Thank you, judges. Thank you.
So now team 11, you can raise your hand. Okay, fine. Okay, I guess only 3 are there from team 11. Okay, fine. Okay, one more. I have added all the 4 of you. Okay, so you can present your screen. You can start your presentation.
Hello everyone, this is Team 11 in BOSCH's mid-prep for age and gender detection. Let's start by understanding the objectives, that is, what an ideal solution here should comprise of. Firstly, we need to use the maximum possible information from the video. That is, use not only the face, but also the body information, as well as information between all possible frames in which the subject is present. Secondly, it should have a good FPS. That is, we should have optimizations to ensure almost near real-time playback of the video. And lastly, we should have usable and interpretable results, as well as a pipeline which can be customized depending on the system requirements. That is, if there is a low computational resources system. So the major four components of our system are the object detection and tracking, the upscaling, passing these through the models, and finally combining the results in the inference stage. So this is an overview of our pipeline. We start with the video frames. We pass it through a YOLO V5 model for multi-object detection. This model outputs two classes, the heads and the bodies. Next, we pass this through an IOU filter, which helps us to relate which face belongs to which body, since these are independent detections. We do this by checking the maximum overlapped area. Then we pass this through a tracking algorithm. We use byte track here, which assigns an individual ID to each subject in the frame, so that we can correlate these subjects between frames. The next step is the upsampling module. In the upsampling module, we have low-res faces which are transformed by a SWIN IR model to high-res faces. However, we do have an optional skip step here in case FPS is important or the input video is of high HD quality. The user can specify this as an argument in our pipeline and skip over this step to save time. Here, instead of passing the entire frame for super resolution, we only use the faces, since these are the most information dense areas and are the most important places in the frame. Next, we move on to the models. Here, to improve speed, we used a concept of batching. That is, we first separated all the faces and all the bodies in the frame. Then we batched them and passed them at the same time to the model to improve inference speed. This drastically cut down our inference time and improved our FPS a lot. We also used a multi-headed model with EfficientNet and SWIN with a coral layer for prediction of age and gender from the face, whereas we use the body only for gender prediction using the SWIN model. And in the last step, we combine these results, we average them over the frames, and we also use the concept of dynamically sized age buckets around these accurately predicted intervals to make our results more robust. Let's go over these modules one by one. First, we have the object detection and tracking. So we use the YOLO V5 model. This is the state-of-the-art multi-object tracking model. And we fine-tuned the YOLO model. Since YOLO outputs 1,000 classes, we fine-tuned it on the crowd human data set, which is a data set of humans from CCTV footage, which is exactly the problem we have. And we used only two classes, which is the heads and the bodies of the subjects. Next. We used byte tracking algorithm. We tried multiple trackers, but this seemed to perform the best. That is, it had very stable re-identification IDs across frames. And as you can see in the graph, it has one of the best FPS and score on the multi-object detection benchmark, MOTA. Next. And we used IOUs to assign each head to the bodies in the frame, if possible, by checking the area of overlap. Next.
One of the major steps in our pipeline is the upscaling of the images before passing in the classification model. As it was hinted to use SRGAN, we fine-tuned the pre-trained version of SRGAN on the IMDb face dataset. We found out that the SRGAN performed well, but the SWIN IR model, that is the state-of-the-art model, performed much better. As you can see in these images, SWIN IR is outperforming the SRGAN model. SWIN IR is a SWIN-based model that is current state-of-the-art, and it also has a fewer parameters. To increase the one more thing that we introduce as a novelty is that to increase the FPS rate, all the faces and the bodies of a single frame are passed as batches instead of single images. One more thing that we added is, in a normal way, 8 gender classification models are trained on the dataset selected, but we are training our models on the outputs of the SWIN IR. This way, the classification models works well at the inference time.
Let's now look at all the models which we have used for training. So first is the SWIN transformer. It's the state-of-the-art image-based transform model, which outperforms all other CNN-based models with minimum number of parameters. We have trained a total of 2 Swin transformers for our case. The first was trained on the outputs of Swin IR, which was trained on the UTK face dataset for combined prediction of age and gender. The second Swin transformer was trained on PETA dataset for prediction of gender based on body images. Next, ordinal regression. So if we treat the age prediction as a multi-class classification with total of 100 different classes, there are mainly 2 problems. First, as the number of classes increases, the accuracy of the model decreases. And second, 2 classes would not have any correlation between them. So to solve this, we treat this task as an ordinal regression task. Ordinal regression means predicting relative rank classes. That is, classes near the true class will have higher probability and consistent classification scores. So to implement ordinal regression, we have used the Coral layer. So Coral is a framework and it can be applied as a layer at the end of any model. So Coral, what does it do? It takes the outputs of the penultimate layer of the model and applies ordinal regression to it with its own loss known as Coral loss. It gives the output probabilities as a cumulative distributive function of the ranked classes. Next, we have used a multi-headed layer. So we know that the Swin transformer is a very complex architecture and it takes much time to train or to inference from it. So to reduce time, we have attached 2 different heads to the outputs of Swin transformer. One head contains Coral layer and which helps us in predicting age, while the other head helps us in predicting gender from the faces. It reduces the training as well as prediction time by much amount and also increase the scores for both the tasks. So now we'll look at all the different scores. So as we can see, as our age detection is a task of regression, the mean absolute error, and for accuracy for gender. So as we can see, the multi-headed Swin Coral outperformed all other models with mean absolute error of 5.294, and the Swin models has given the accuracy of 94.2% from face and 94.4% from the body images. Next, let's look at all the datasets which we have used for our task. So the crowd human dataset, the IMDb face dataset, the IMDb dataset, UTK face dataset, and PETA datasets. So next, we will have some of the images from these datasets to give what these datasets contain.
Let's move on to the inference part. Finally, after taking the information from all these different places, we need to combine them so that we're able to get good predictions. For this, we use dynamically sized age ranges as one of our novelties. What this does is, since we have treated this as an ordinal regression task, we are able to get probabilities around the true class in a consistent way, such that we are able to predict ranges around the true range depending on how confident we are. So if we are highly confident, we will predict a very narrow range around our outputted prediction. And if we are less confident, we will predict a larger range. Since the problem statement required us to do either of the two, we thought it is better to use both of them since the results can be better used, which was one of our objectives. Next, we average over all the frames. Certain times, certain people aren't fully seen, or they are occluded, or they are hidden by certain other reasons. So we take the average over the predictions through all the frames since we are tracking the ID. And for gender, we take the mode over all the frames. Hence, we are using maximal information, which was our objective. Lastly, I would just like to go over all the novelties that we have used in our pipeline. We have used the state-of-the-art bite tracker, which performed well after trying multiple trackers. We got stable age predictions by taking a continuous average over multiple frames, as well as taking the mode over for the gender over multiple frames, hence using most information. We also used the body features were useful because body would be useful to predict gender more than it would for age. Then we used Swin IR instead of SRGAN after trying the two because Swin seemed to perform better on videos on resolution. Then the models in our pipeline, instead of being trained on the dataset itself, they were trained on the dataset after being passed through the Swin IR. Since every upscaling algorithm has certain artifacts, this helps the models to learn better based on Swin IR's output. We used a multi-head classifier so that only single inference is required for both age and gender, which reduces speed a lot. We used coral layers for making the task an ordinal regression task. And finally, we used dynamically sized age ranges. Thank you.
Thank you, Team 11. So now I want to ask few questions. Can you go to your novelty slide? Uh, so so bite tracker you're using, okay, for tracking humans. What was it novel about it?
We tried multiple trackers, and since it was one of the newer, most like one of the latest trackers, not very recently used, we introduced it as one of the novelties in our pipeline.
Okay, and regarding the PETA dataset, so you have used IMDb face dataset. Okay, that is okay. But the problem statement, it is more correlated with the PETA dataset, right? I mean, I don't know whether you have placed it in your in this or not. So how is SWIN IR for super resolution? How is it performing on PETA dataset?
Yeah, so basically we tried running it on PETA dataset as well. So what we saw is like the facial features were not we were not getting the good facial features because of SWIN IR, and also in SWIN SRGAN also. So basically the PETA dataset, when we passed through the SWIN IR and SRGAN, so basically all the clause and the other attributes were good. Their super resolution was good, but the facial features were like not that good. So like we haven't so when we are predicting gender from the images using the body, we are not passing it through the SWIN IR.
And just to add to that, it was we used this for fine tuning our ready GAN models. So here we just needed any data set which we reduced the resolution and then trained it. So IMDb, since it had good facial features in that, we reduced the resolution a lot and then used it while fine tuning our SR GAN models.
So why I am asking you this with reference to the Team 10 presentation, if you have seen the super resolution they have used for PETA, no, it was not working. So that's why I wanted to know whether it was working in your case or not with SWIN IR. Because for IMDb and Crowd Human and UTK face, the things are, the faces are there. You can see the faces, but in the PETA dataset that that is more correlated with the problem statement right now. So it should be like I don't think it would work. I mean okay, I don't know whether it would work or not. And one more thing,
So PETA is also full body. In that,
No,
only since we are only upscaling the faces, this was not the data set on which we checked it. But if you see our result slide, we tried using the with and without super resolution, and on face age detection, the accuracy is improved drastically while using super resolution. So I'm not sure about Team 10's result, but for us, at least in our comparisons, we could see that using this improved the predictions on almost all data sets we tested on.
Yeah, and like when we applied SWIN IR to the PETA dataset and like trained the SWIN classifier, so like the accuracy was not increasing very much, and like it was just 0.1 and 0.2%. So to say like to increase the FPS, like we are not passing bodies through the SWIN IR.
Okay. And how many FPS are you getting in the output?
Yeah, so with SWIN IR, basically there are two options. So like we can we can have video with SWIN IR and without SWIN IR. So with SWIN IR, the FPS is 15, around 16 FPS, and like without SWIN IR, it's around 40, 42.
Okay, with the SWIN IR, it is 15, and without, it is 40, 42.
Yeah, yeah.
Okay.
Yeah, team, can you explain that coral layer? Can you?
Yeah, so we are not treating this as a classification task. We're treating it as an ordinal regression task. What that means is in classification, every output layer, like 36 years old and 35 years old, would be treated as independent classes. Instead, the coral layer, we took it up from one of the papers on using a consistent rank adjusted logits. Its outputs are consistent. So the output of every particular node, as seen in this diagram, is basically the CDF, which is the probability of getting probability of the image having an age greater than R1 in any of these. So that the output is a CDF, and it is consistent. So if your predictions are closer to a particular age of say 33, around that age you'll get high probability ranges. So that's the coral layer, and it
So
has this specific loss, coral loss.
okay, so coral layer is doing nothing but converting everything into CDF, right?
Not only converting it, it's a complicated step. It basically uses a weight sharing, and it uses independent biases, and the output is definitely a CDF, but it's made in such a way that the output comes as a CDF. It's not artificially introduced or artificially you're adding up all the logits to make it a CDF. The loss function is written in a way that you're able to get them as consistent ordered logits.
And it is trained to backprop only, right? The weights.
Correct. We add it to our final layers and we train it to backprop using the loss
coral loss.
Okay. In the penultimate layer, you'll be having how many units? Is it 101 or
how many?
In the penultimate layer of Sven model, we are getting total of 1024 features.
Okay. Okay, here in this one final one, how many categories? Yeah, after the penultimate layer.
After the penultimate layer, if we treat it that as a classification task, then we will get different categories. But our coral layer treats it as an ordinal regression task, so we won't be getting any number of categories. We'll just get an output which would give us the CDF of ages, and we'll get a single age number.
Okay.
But the number of classes, if we had to, it's an architectural choice, and we chose it to be a range from 1 years old to about 82 years old. So.
Okay.
Okay, hello team 11, this is Janvi here. First of all, thank you for the wonderful compilation of your presentation. I really liked it. So one question, do you see any impact of the current scenario of surveillance where people are wearing masks over the approach that you have taken?
So we thought about this. That is why while fine tuning our YOLO data set, we specifically chose heads and bodies as classes rather than taking face and bodies as classes, which a lot of the other tracking algorithms may miss. So in this case, we are even though some parts of the face will be occluded, we are able to get, even like wearing hats, etc. We are able to at least draw the bounding box around the face, and our model gives outputs on that, though it may not be as accurate. Secondly, we are also using the whole body, not just the face, like a lot of people, because then at least even if our age predictions may not be accurate, which it wouldn't be that much when your face is completely covered, at least our gender predictions will be on point because the rest of the attire is seen and few facial features are seen. So this is why I think our solution is more robust than most for the current scenario.
Understand. And are you also considering any, see, because you're already using tracking here, is the tracking used just for correlating people between these scenes, between the frames, or are you also using certain cues from these temporal data to have better accuracies on your age and gender, or stability in your age and gender prediction?
We are using it mostly to combine information between frames, and we are taking the average over those IDs between frames. So we are kind of using information. So if we track a particular ID, we append all the ages predicted.
It's only the, sorry, but I think what you're using is only combining of results. What the question is, are you taking the feature cues or the data cues to end up with the results?
No.
Okay. Any reason that you have skipped it, or it was just a time, or you thought that it might not be the value add.
Yeah, we did not think it would be a very viable approach, and this seemed to be working well enough. One improvement which we could definitely add on this is, instead of taking just simple averages across all the frames, for good feature extraction, we could also use the confidence in particular predictions and take those averages, because we shouldn't give equal weightage to, say, an occluded face and a fully seen face. So that could be part of our future works.
Anyway, that was part of my next question, so I think you answered it. Yeah, that's all from my side.
Thank you.
Okay, then we can move on to the next team. Okay, so next team, team number 1, you can raise your hand.
Okay. Can you confirm?
Okay, so all the members are there from team 1 on the stage. Okay, you can start your presentation. Yes, your screen is visible.
Hello, team 1.
Good afternoon, everyone. We
Yeah.
are team 1.
Sorry. Just a second, team 1. You know the instructions, right? The presentation should be of 10 minutes. It will be followed by the Q&A session of 5 minutes. Yeah, right. Yeah. Yeah. Okay. At the end of 8 minutes, we'll be pressing a buzzer to remind you that 2 minutes are left. Right. Yeah. Okay.
Good afternoon, everyone. We are team 1 and we present an end-to-end solution for the age and gender prediction of people from surveillance camera feed, taking into account the low resolution and the height of the camera for surveillance. Our model's pipeline is as follows. The video inputs from surveillance cameras are fed into the model. Then, from each frame of the input video, faces are detected using MTCNN. Afterwards, the cropped face images are fed into our pre-processing pipeline to improve the quality of the detected faces. We have applied two age and gender prediction models, a classification model and a regression model. We take the weighted average of the predictions made by these two models for better predictions. Lastly, the output is generated in form of annotated videos as well as the required CSV files. Let us now look into the details of each step mentioned above. The input test video. We have some standard sample videos provided by the company, as you can see on the right, along with our custom-made videos for testing. One of them is shown on the left.
Out of the numerous face detection models that are available in the literature, we experimented on the following 4. Media pipe face detection, MTCNN, YOLO V3, which was fine-tuned for face detection, and retina face. After conducting experimental surveys on all of these face detection models, we inferred the following results. MediaPipe, despite of its blazingly fast speed, performed extremely poor when it came to accuracy for distant images, that is, images for surveillance camera. YOLO V3 performed extremely well in terms of accuracy, but it was slower when it was integrated with our model. And MTCNN and Retina Face gave decent results in terms of both speed as well as accuracy. So why MTCNN? The face detection metric that we used for 75% visibility of face in each frame was the visibility of both of the eyes of the person, irrespective of the face alignment. So MTCNN performed well with respect to our defined metrics in terms of speed as well as accuracy. Why not something else? Retina Face, despite giving equivalent or better accuracy than MTCNN, had slower speed. And also, we could have deployed it if the metric for face visibility was lesser than 75%. We tried YOLO V5, which is the state-of-the-art object detection model, but its face detection model is not publicly available. And applying a different face detector over the person class from YOLO V5 would have drastically reduced this model speed.
Now, even after taking input feed video of 720p resolution,
The size of the detected faces which were inputted to the age and gender model is relatively small, approximately 40 by 40. Resizing it to the required size for age and gender model deteriorates the quality, which impacts the projections negatively. Hence, upsampling is really required. The intuition for using bilinear interpolation was that it might be easier to first upsample the low resolution image using traditional methods. Then we can finally refine the resultant image by using ESR GANs. Consequently, we resize the image for our regression model. At the same time, we use DNN module for classification module as we often get higher FPS with the DNN module, which is also backed by various research. Now coming on to why ESR GANs. Interpolation method works good, but the results are a bit unsatisfactory. As we all know, humans don't distinguish image by pixel difference, but rather by perceptual quality. GANs in generally increases the perceptual quality of the image, or in other words, it makes the image more pleasant to the eyes. One of the major reasons that ESR GANs works so nicely than SR GANs is that it consists of various loss functions rather than a singular one. Its research quality is backed by an astounding number of 1656 citations.
After getting the super image, now we have to predict the age and gender of detected faces. The super resolution image is passed in two models, one classification and other regression, which works independently to give respective projections on age and confidence score. The gender prediction is solely based on the classification model, as it's a by-class problem. After getting the respective projections of age from the two models, we finally combine them by taking a weighted average of their respective projections to give the final predicted age. Moving forward, the weight of classification model is its confidence score, and the weight of regression model is 1 minus confidence score. Now let us suppose that our classification model has high confidence on its prediction. This means that the final age is in the class predicted by classification model. Suppose the class is 14 to 20. Now here the role of regression model is to determine where the final age lies, towards 14 or towards 20. Second case, what if the classification model has a low confidence? As our classification model is not much confidence on its prediction, so here weighted average of both models' predictions is used to give the final output. Although there are various hybrid models present in age prediction literature based on classification and regression, but as far as we know, the weighted average technique using both models that we used in our model is very novel. The classification model used is based on Levi and Heschner model, which is trained on Adian's dataset. It is cited by 1134 papers, which justifies the prioritization of its confidence score. The regression model used is based on a blog by Abhisit Roy. It is a 5 convolution layer deep regression model. For evaluation, we use subjective metrics based on human perception for all our models, including face detection, super resolutions, and age and gender predicting model.
So here we have attached our video snippet in which two of the females have been identified and their ages have been predicted to be 29 years old. And a similar CSV file snippet is also attached in which these the results from these video snippet have been added. Now, our model is doing a decent job, both in terms of speed as well as accuracy, but we think that a lot of improvements can be done to this as well. For example, a YOLO V5 face detection model, which is currently not available, can be deployed. Then we are currently using a generic image super resolution technique, that is ESR GANs. Specialized SR GANs or any other technique for faces can be trained and implemented. Moreover, currently our model is not performing well when it comes to ages above 40. And that is due to the imbalanced data sets. That the ADN's data set as well as UTK phase data sets both are imbalanced. Uh, The other thing is that model's accuracy can be improved for faces below 75% visibility. Although in the problem statement, it was not, it was mentioned that faces for only with greater 75% visibility will be used for evaluation. And at the end, an end-to-end model can be trained and implemented on a balanced data set, and which is one of the future prospects. Thank you, and we are open for questions.
Thank you, Team 1. Judges, you can start with the Q&A session.
We are open to any questions now.
Judges, can you hear us?
Yeah, sorry.
Okay.
Can you go back?
Yeah. On which slide?
I think the second last one. No, not this. I think before this. Okay, before this also. Go back.
This
Yeah,
one?
this.
Yeah.
Okay. Okay. Go back. Go back. One slide more. Yeah, this.
Okay.
So after having the super resolution image, you are feeding it into the classifier, that is a gender classifier. Okay, and the okay. Can you explain me the upper part after the classification age gender model?
Sure, sir. We are using two different models, like classification model and regression. So in the upper model, classification model, it gives us both an age class range and a confidence score related to that age class, and a gender output. So then we are using it says output and the regression model says output, and calculating a weighted average of the two to give our final predicted age. So is it clear now, sir?
Okay, so okay, okay, in the upper classification layer, what is the size of the output layer? I mean, how many nodes are there?
Yeah, so basically around 7 classes are there, one from 0 to 3, then 4 to 10, then and moving forward in this way. And for higher ages, it is directly predicting 60 to 100. So that is why it is currently not working well for higher ages above 60.
Okay, and you have also, apart from 7, there must be a node for gender also, right?
Yeah, right.
So a total 8, right?
Right.
Okay, then after getting the classes, like, so for example, as you have explained, suppose the 14 to 21 is the range I'm getting, okay, after classification. Then you are doing the regression analysis on that and finding out what is the exact age, right? Is it?
No, sir, it's not actually completely correct. For understanding this, like there are two cases. If our classification model is confident, like more than 70% confident on its predicted class, then it will we will apply regression on that class range. But if it's not that much confident, then the regression model is working independently. It has given its own prediction on the age. So then we are calculating a weighted average of the center of the median of our output class and that predicted age by the regression model. So we are working on with the confidence of the classification model.
So the center point you are taking, okay, for the range for 14 to 21 is must be 17 or 18, right?
Right. Exactly.
And what is the FPS output FPS you are getting?
So currently, when we tested it on our CPU, then it was giving around 1 to 2 FPS speed. But if suppose it is if it is tested on a GPU, then a higher FPS can be achieved. And also, if suppose you have to improve the FPS when it comes to the CPU, we also had a skip frame code ready, although we did not give it to you. And in that skip frame, you can just sorry.
Yeah,
Was this?
go ahead.
Yeah. So using that skip frame, you can skip 3 frames, and we understand that if you skip 2 or 3 frames, then not much temporal difference is there between a person in the first frame and the third frame. So in that way, we can increase our speed when we are testing it on CPU as well.
All right.
Yeah.
Hi team. One doubt. Can you move to the previous slide?
Just a second. I think yeah. Okay. Yeah.
Yeah. This one. So here, this classification age gender model, is it a multi-head one or is it a single head? Because see, you have age and gender, right? Is it multi-head or how is it?
Yeah, it is multi-head. It is giving us both age and gender.
Okay. No, multi-head, I mean to say, your penultimate layer will be linked to the 2 heads, or is it a single head at the final? Because
So
see,
actually,
age
they're
and
connected. Yeah. So actually, they are connected to 2 nodes. One is leading to the age part, and the other is leading to the gender part.
okay. Because earlier, when Pratik was asking, you told like 8, right? 8 levels.
Oh, right.
No,
Sorry
no.
for
So
that.
actually,
Yeah.
that's why we are 7. Okay. Yeah. Sure.
So okay.
Janani, anything from your side?
Nothing from my side.
Okay. Thank you then team 1 for presenting your ideas here. I will now request you to please leave the meet so that we can call the next team.
Thank you.
Thank you, team 1.
Okay. Thanks a lot.
Thanks, team 1.
Participants of team 19, you can raise your hand so that we can grant you the access.
Good afternoon. I hope I'm audible.
Yes, you are audible. So from team 19, everyone is joined, right?
Yes.
Okay. So the presentation will be of 10 minutes. At the end of 8 minutes, I will be pressing the buzzer, which will sound something like this. It will tell you that 2 minutes are left and you have to wrap up in around 10 minutes because if you go further than that, there are deductions related to it. And then we'll have a Q&A session of 5 minutes. Okay. All the best, team 19. You can start now.
Thank you. I hope my screen is visible.
Yes, it is.
Yeah. So, good afternoon. We are Team 19 and on the BOSCH mid-prep event, Age and Gender Detection. So, just a quick overview of the problem statement that we'd like to give is that we wanted the problem statement was to predict the bounding boxes from CCTV surveillance footage of people's faces and use that to predict their age and gender. And considering that the footage is low resolution, it typically requires upscaling to get decent predictions. So we upscaled the low resolution footage to get the finer features of the model using a Swin transformer based image processor. And the coordinates of the bounding boxes we extract from the processed image. The bounding boxes are then cropped from the face, and we use a pre-trained VGG model, which was then trained further both for age and gender detection. And the outputs of the age classification tasks are further processed using deep ordinal regression. So this is an overview of our pipeline, where basically given an input image, which is a single frame of the video, we can optionally perform super resolution. So this step can be skipped in the interest of either processing speed or if the video is already high enough resolution. From the high resolution image, we can then do face detection, which gives us the bounding boxes. This then combined with the image gives us the images of each individual face, which is passed through two parallel models, one for age detection and one for gender detection, which are VGG16 based models, and the age detection additionally uses deep ordinal regression. So for image super resolution, we use the MPII dataset, which is which has approximately 25,000 images of people doing various activities. So and it's on a variety of different backgrounds and of people in a variety of different poses and from a different angle. So this really is a kind of representative of the data set that we would be handling actually. So we can train the super resolution model specifically for the features that are required from it. The super resolution model is SwinIR, which is based on a 2021 paper it's a transformer based model for image super resolution. So it has had improved accuracy as compared to traditional convolutional models. Firstly, because it allows for whereas basically convolutional model use the same kernel across the entire image, the multi-head attention framework of the Swin transformer can allow for a better extraction of more high frequency features. And so we have the image describes is a quick overview of the structure of the Swin IR model, where it's basically has three stages: a shallow feature stage, a deep feature extraction phase, and then a high quality image reconstruction. The shallow and the first and last stages are simply convolutional stages, and the deep feature extraction stage consists of several RSTV or residual Swin transformer blocks, which each consist of several Swin transformer layers and a final convolutional layer. So this has had this has been proven to have a really good accuracy on super resolution tasks, even more so than SRGAN, and that's why we chose it for our super resolution framework. For our bounding box detection, we use the face recognition Python library, which has pre-trained models, which uses DLib's pre-trained models for face recognition, and it has been shown to achieve 99.38% accuracy on the LFW dataset. And to ensure consistent face IDs across the video, we use the intersection over union of all the data from the previous frame. So when we in consecutive frames, we compare each pair of bounding boxes to ensure that the one with the that correlates most with the previous frame is assigned the same face ID.
Hi everyone. So for our models for the age and gender prediction, we're using the UTK face dataset to train them. And so the UTK face dataset, it has around 20,000 unique face images with age and gender labels ranging from 1 to 116 years in different poses, lighting, ethnicities. And so the model we used was a pre-trained VGG16 model, named so because it has 16 convolutional layers and has historically had a very good accuracy on such tasks. And so the gender detection was a simple binary classification task. So we pre-trained a VGG model, 16 models separately for that. Whereas for the age detection, since we decided to, since the output format given to us required us to predict the accurate ages as well as certain intervals within which that we expect the age of the person to lie. We used deep ordinal regression to sort of get an ensemble model to estimate the age. Okay, yeah. So deep ordinal regression, as can be seen over here. So once we have our CNN backbone consisting of VGG16, we had different partition sets consisting of different bins with varying widths, but which all encompass the entire range which we have, which is 0 to 116 years. And so we backprop through each of these softmax layers. Since the CNN backbone, it gives us around so we backpropagate through all these layers, and yeah. So the loss function thus becomes so for the loss function we take the values in which the values in which the true label of our age actually lies. So the QN D subscript L part over here is one only for the bins in each partition set where our age where the true age lies, whereas the log part of this equation of this loss equation tells us gives us the logarithmic values of the softmax probabilities, and this is done across all such partition sets for all the bins that our true value corresponds to across all the images that we are taking into consideration. And so we obviously need to maximize this loss function. The prediction is thus given by thus given by taking a weighted average across across all the probability across all softmax values across all the bins to sort of get an ensemble. So it sort of acts as an ensemble model, giving us a much more a realistic prediction of the ages. So coming to the drawbacks, the model, especially the Swin transformer, had a relatively high GPU usage. And obviously, the next thing was, since our model, it relies on the IOU values across successive frames to detect the person and give out the person ID attribute in the CSV file. If the person's face is somehow obstructed in between the frames, the different person IDs are given to them, so we cannot really track the particular person if their face is somehow obstructed, since the prediction model uses their face for image super resolution. It takes a lot of time for the photos with high resolutions as expected. That's why we have given an option to the user if they want to upscale their image before prediction, as Ayush rightly mentioned. Future scope, we think we could use a gender as a once you've detected the gender, or since you already know the gender in the once you've detected the gender, we could use it to detect which could somehow be useful for detecting the age. There are certainly better models for age and gender detection. We had to use VGG16 due to certain constraints owing to time and processing power we had, but there can certainly be better models that we could have used. Again, transfer for computer vision, it's a really hot field right now. Gained traction mostly last year. The Swin IR model that we use, it was released. It was introduced in a paper in the August of last year. So, given the recent developments, certainly in the forthcoming future, there might be better models based on transformers for computer vision. So that wraps up our presentations. We are open for questions now.
Judges, you can start the Q&A.
Yeah, hi Team 19. So can you briefly explain me about the regression and classification that you are doing?
Okay, so what's happening over here is we have, so considering the fact, usually, let's say we had to convert this whole regression problem into a classification problem. A very naive solution would be to partition our age range from 0 to 116 into, let's say, L number of bins, right? So what we have done here is we've made m such number of partitions with an equal number of bins. So let's say let's assume the age range was 0 to 9 for us, right? So one partition could have bins of 0 to 3, 3 to 6, 6 to 9, while the other could have 0 to 5, 5 to 7, 7 to 9, right? And so we have randomly assigned these values, these bin values to each of the m partitions we've taken. So we took 10 such partition sets, and each partition and in each such partition sets, the whole range is divided into 10 classes. And so what we're doing is so we have a softmax layer for each of these partitions, and then we're back propagating through them using, and the loss function uses, if you skip to the next slide, the loss function used is as such. So where QNDLM is essentially a one-hot encoding that says that our the target value for a particular image it lies, if it lies in that particular class, we're only taking then only we're taking the log of the softmax probability of that particular class, and then so we are doing it across all the m number of partition sets that we've taken for all the data points in our batch.
Anshul, so this is the log of probability of D, that is a range condition on that is data, right?
Yeah.
Okay. So it will be a output of softmax, or are you considering? Are you
No,
approximating?
it's a softmax probability value. So across all the bins, it should sum to one, right? And we're only taking the softmax the log of the softmax probability of the bin in which are true class lies, true age lies.
So can you go back again?
Yeah.
And
so let's say we have.
Can you go?
Yeah. Okay.
The whole pipeline, are you?
Yeah.
Okay. Do you have somewhere?
Yeah.
Okay. The image super resolution. Okay. As super resolution image face detection, bounding boxes, and from those bounding boxes, the face images are there. The gender detection is the classification problem, right?
Yeah, it's a binary classification, so we have separately
And
trained a
you have a separate network for that.
Yeah,
That's
we have
what
a
I'm
separate
asking.
network for that. Yeah, it's separate.
And for age detection, you have used ordinal regression. Okay, you
Yes.
have these 10. Okay, can you go to the next on that slide, ordinal regression slide? Okay, so X, it goes to a CNN. Okay, and then it has 10 branches. Okay, and these 10 branches are outputting some probabilities, and you have the loss function for that, and you are doing the regression analysis.
Yes.
And what is the output FPS?
Sorry, sir, could you repeat?
Output FPS you are getting? I mean, what?
So with for without processing with the Swin IR, it's around 30, and with I think it's around 10 to 15, depending on which system we use. But yeah.
Is 30 FPS, right?
Yeah.
With IR, it
without image super resolution.
Without image swim IR, and without it is 30, and with it is 10.
Yeah.
Yeah, thank you, team 19. Vinod, do you have something?
Can you go to the next slide?
Yeah, is this the slide you want us to go to?
Hello, Vinod sir. I'm not audible.
Oh, sorry. Yeah, your doubt is like how you will be back propagating it.
Yeah. So
since you're converting that to your bin, right? Then you are using the softmax.
Yeah.
Yeah.
So okay, so we have softmax layer for each partition set where we have sort of divided them into bins, right? And so the capital M here stands for the number of such partitions we have. So if you could, Ayush, if you could go to the previous slide. So as you can see, there are different softmax layers, right? So we back propagate through each of them, and the loss function used is the one we showed in the next slide.
Okay.
Yeah, so if I could just try and clarify, basically, with each softmax layer corresponds to a set of 10 bins over our range of 1 to 116, and in each we basically classify the age into each softmax layer. Basically, gives us the probability that the age lies in each bin, and our loss function
So each
says.
softmax is a bin, right?
No, sir. Each softmax is a set of bins, is a set of 10 bins.
Set of bits.
So,
Okay.
and all bins, and each set is uniformly randomly distributed. So, for example, one bin set could be 0 to 20, 20 to 25, 25 to 75, and something like this,
Okay.
something like that. And
Okay.
there
So
are 10 such sets
this
of
kind of
bins.
how many softmax you are using?
10 such
How
softmaxes,
many?
sir.
Okay.
And each softmax has 10 outputs.
Okay.
So, so each softmax basically gives us a set of probabilities that the age of that person lies in each bin. And for training, what we do is we take the true bin that the age lies in, and sum all for each such set of bins, we sum the log of the probability of the true bin. So, for example, if our age was 75, then for each softmax layer, we take the bin in which 75 lies, take the log of the probability of that bin, and sum all of it. So we want to maximize this value. So there's we negate this sum, and that becomes our loss function.
Okay. One question. So consider the age of a person is 25. So it can be in only one bin, right? Or even it will be in all the 10 softmax it will be there.
So each softmax layer corresponds to the entire age range, and it
Entire
divides
age
the
range. Okay.
entire age range into 10 different ways. So it will that 25 age will lie in one bin in each softmax layer. So for each softmax layer, we sum the log of the probability of that bin.
Can
So
you
like
repeat again? Each softmax belongs to one age group, right?
yes, sir.
So
So
consider
yes.
like for example, first softmax belongs to 1 to 25. Okay. So
No,
then
sir.
in that some 10 bins are there. Like
So
then
the each softmax corresponds to the entire set. So if you look at this
entire set.
diagram
Okay.
on the right side, so you can see that there are like D1, D2, D3 are the kind of sets of bins, the number line, and it has been partitioned into each bins. So if we consider a value, it will lie in one bin in each such D1, in one bin in D1, in one bin in D2, and in one bin in D3, and so on until, for example, D10. And so we the model outputs the probability that the face has the age in that bin. So we take the true bin. So for example, if we know that the age is 25, so we take the bin that corresponds to 25 in each softmax layer, and we sum the log of the probabilities in that bin for each bin.
Okay. Yeah. Okay. Yeah, thanks for the explanation.
Thank you, sir.
So hello, team 19. Judges, is the Q&A over for team 19?
Yes, yes.
Yeah.
Hello.
Yes. Yes.
Okay. Okay. Yes, sir. Okay. Team 19, you can leave the meet. Thanks a lot.
Thank you.
Yeah, thank you for having us.
Team 8, you can raise your hands so that we can grant you the access. So team 8, everyone has joined, right?
Only 3 of the members are available because the other 3 members had an industrial trip today. So we 3 will be presenting an answer mark.
Okay, it's fine. So I'm just repeating the instructions once again. You will be having 10 minutes of presentation. At the end of 8 minutes, a buzzer will be pressed, and it sounds something like this. We'll tell you that 2 minutes are left, and the limit is 10 minutes. If you exceed that, deductions will be applied. And for the Q&A, after that, we will proceed to the Q&A session, which will go around for around 5 minutes. So, teammate, all the best. You can start your presentation now. Teammate, you're not audible.
I'm so sorry. Can you please restart the timer? There was some issue
Yes,
with the
yes,
mic.
yes. It's
Okay,
fine. You
thanks.
can start again.
Is this slide visible? Yeah. Good evening, everyone.
Yes, it
We
is.
are from Team 8 and we are here to present a solution for the BOSCH agent general detection problem. I am Ananya and I'm here to present with my teammate Drishti, and Jitesh has joined us for the question and answer session. These are the contents of our presentation. First, explaining the problem background in a gist. So there are several advantages of developing automated video surveillance pipelines because humans have a limitation in their ability to analyze multiple activities together. Person tracking and attribute detection from videos can be quite useful for crime footage analysis and crowd modeling, with age and gender being two very important attributes which can help us in person re-identification and recognition. And even though there's a scope for a lot of improvement via further research, but with the right research and data sets, we can also tackle the gender and racial bias in AI algorithms. We can deal with low resolution footage and also deal with videos which are captured from cameras placed at a height, which can be sometimes difficult for humans to do. Talking about our pipeline, so we are doing the following. We are tracking the people and assigning a person ID to each person in the video so that they can be tracked throughout the length of the video. We are obtaining a bounding box around the person, and we are also doing face extraction. Going into the detail of a pipeline, so the main components of a pipeline are as follows. First of all, we have used unit track for person bounding box, capturing the bounding box around the entire person, along with assigning a face person ID to each person so that they can be tracked throughout the video. Unit track is a state-of-the-art object tracking and detection model. Then we have used a ResNet-based face extractor. So every individual bounding box obtained around in every individual human is fed through this ResNet-based face extractor model, which is basically drawing a bounding box around all the faces which might be present inside a single human's bounding box. We have used this because there are cases when the video might be of that of a crowded region, and in that case, inside a single person's bounding box, multiple faces can be present. As the next step, we have basically fed individual frames of the video into a retina face based attribute predictor, and this pipeline of retina face plus MLP based layers which we have used is outputting the age and gender of the person corresponding to each face, along with giving us a bounding box. And finally, to tackle the problem of assigning this age and gender to the person who is being tracked, i.e., to the person ID, we have basically taken an IOU between the faces obtained from ResNet and retina face so that ultimately every person has an ID, age, and gender assigned to it. Finally, a pipeline is outputting the person's age, gender, a bounding box around the person, a bounding box around the face, and the person ID. Now, a small note as to why did we not use super resolution in a pipeline. So we tried several super resolution models like SRGAN, SRSNet, TechoGAN, WDSR, etc. But we noticed some drawbacks in all of them. Common drawbacks being that they are generally capable of just increasing the size without loss of quality, but as such, no observable advantage was observed in terms of the increase in the model's performance, improvement in the model's performance. It just increases the time taken, and moreover, we were told that the videos would be of a good quality, that is more than 720p, which we thought is already a good enough resolution, and hence we decided to do away with super resolution, even though we have also provided an optional code in our pipeline, and if needed, the videos can be tested with it. And we also tried some GAN-based models like Pulse, which is capable of hallucinating fake details from a blurred face. But it was also not useful because in some cases it was even switching the gender of the output produced. Hence, we decided to do away with those components. This is the system architecture diagram. So first, an individual video is broken into multiple frames. The frames are fed into the unit track model so that the person can be tracked throughout the video. And it is also returning bounding boxes around the person. Then we have also fed these frames into the retina face-based model, which is drawing a bounding box around each face present in the frame and also outputting their age and gender through the MLB-based layers we've added on top of it. And these are all pre-trained models. And finally, to assign the age and gender to the person ID, we have taken an IU comparison with the outputs of the ResNet-based face extractor, as it was explained on the previous slide. Now my teammate Drishti will be taking over.
So the reason that we use unit track is because of its generalizing ability and task agnostic nature for object tracking, which can be learned in a supervised or a self-supervised fashion. Also, it gave outstanding overall results, and the same were mentioned in the research paper published in Europe's 2021. Secondly, for our age and gender detection model, we use a retina phase backbone, which produces state-of-the-art phase detections, on top of which we insert MLP layers with IC layers combined with them. IC layers is simply a fancy term for adaptive batch norm and dropout on top of the detector. We have separate heads for both age and gender. So there's a separate regressor loss for age and a classifier loss for gender. Moreover, for age, we have separate bins made because the output asked for both number and a range. For the range, we dynamically allot a range to each number based on how old or young the person is. For example, for the ages around 5, we'll give the range based on a smaller bin size. So we'll have 5 to 7. And similarly, for an older age, we'll have a larger bin size. So that would be 70 to 100. So keeping that in mind, next. This is simply an overview of the model architectures. Nothing to go in depth over here. Next. Right. So there were certainly some problems that we faced in our pipeline. Firstly, there was the problem of multiple faces in a single bounding box. Our solution over here was to extract the face confidence scores that our face detection model had given to us, and all the confidence scores that were above a threshold hyperparameter, which we hard coded as 0.25, were kept into consideration, and the maximum confidence face was extracted. Secondly, there was the problem of keeping the person ID consistent throughout the video. Now, what our retina face model does is that it gives us accurate age and gender predictions, but the age and gender predictions are not allocated to the corresponding person ID. For the same, what we need to do is that the facial bounding boxes that are given to us by retina face are compared with the facial bounding boxes that were given by Unitrack. So after the comparison is made by finding out the maximum IOU, the corresponding result is allocated to the person ID. Next. So there were some experiments that we really wanted to perform while creating this pipeline, but couldn't due to computational restraints and time restraints. So like one of those was for age classification. So we really wanted to experiment with the usage of disentangled facial attribute representations through contrastive learning. Why we believe this would have helped was that we could have customized the losses to have certain age clusters together and certain age clusters farther than those. For example, especially for Indian faces, the age ranges from 30 to 50. You can't really distinguish between them, but you can distinguish between the combined age clusters of 30 to 50 and the combined age clusters of 70 to 100 quite easily. So our losses would have minimized the distances between the age clusters from 30 to 40 and 40 to 50 and maximize the distance between 30 to 50 and 70 to 100. And also for gender classification, we believe that the body can also be pretty indicative of the gender of the person, but we only relied on faces over here. That was mainly because we could not find an appropriate data set for gender classification on body. The dataset PETA is not available for commercial uses. Hence, we could not use it for our purpose, and it was clearly stated in the rules that only datasets for commercial purposes are allowed. So that is it for our presentation. These are the references and the motivations for our solution. Any other questions are most welcome. Thank you.
Thank you, teammate. Jairus, we can start with the Q&A session.
Yeah. Hi, team. Can you move on to the architecture?
Sure.
So this face extraction, how you're doing it?
So we are basically using two models for that purpose. The retina face-based model, it is basically configured to use only images of a particular size. So the unit track is outputting bounding boxes, and obviously bounding boxes for different people can be of different sizes. So hence, instead of feeding the bounding box to the retina face, we are feeding the entire video frame to the retina face, and it is outputting it is making predictions on all the faces inside the frame. And at the same time, we are also using another model, as we have explained over here, the ResNet based face extractor, which is basically taking inputs of the individual bounding boxes around the person. And then this is used so that we can associate the person ID with the age and gender. And then we are taking an IOU between these two outputs from the ResNet based model and the retina face based model.
Okay. So basically you are using unit track as well as the retina face extractor. Okay, unit track to detect the object, and yeah, retina face extractor. Okay. Then from unit track you are getting the face through this ResNet face extractor, right?
Yes, sir.
Okay. So then you do the IOU between both. Okay.
Yes, sir.
So you could able to match the IDs. So what? So is there any metrics available for the one?
So unfortunately, we could not evaluate a pipeline quantitatively because it is built kept in mind the video inputs and outputs, and we could not find any annotated data sets on video which have the age, gender, and the IDs which we need. However, we have used pre-trained models for all the purposes. The reasons being that these are trained on very large data sets, and like the outputs which are currently available, further fine tuning we believe could not have caused any further improvement. So since these are already pre-trained models trained on very large data sets, hence we could we did not pursue much of quantitative evaluation, along with the reason of course missing annotated video data.
Okay.
However, we did check it qualitatively on a few videos.
Okay. So Pratik, you have any questions?
Yeah, sorry, I lost in between. But
okay.
Yeah, so as far as I could understand, Team 18, so you are using Unitrack for bounding box, and then you're using retina face for face detection. You are comparing the IOUs with the one that the bounding boxes you are getting from ResNet face extractor, right?
Yes, the unit track is outputting the bounding box around the entire person along with the person ID. So it is helping
Along
in
with,
tracking
okay.
the person throughout the video.
Can you go to
Hello,
the
sir.
architect? Yeah, Samar.
Sir, just a clarification. It's team 8, not 18.
Oh, sorry. Okay, team 8. Okay. My bad. Sorry. Can you go to the architecture, please? Okay. So unit track models you have detected. Okay, and face and extracted and mapped as a person ID. IOUs comparison to associate each face. Okay, so you are using different network for age and gender predictions or same network?
So we're using the retina phase backbone for both age and gender, but on top of it, we have separate MLP layers and separate losses for both age and gender.
Okay. And what is the FPS, output FPS you are getting?
So we're getting about 10 seconds per frame. So like we did it for the entire video, and the video was about 2 minutes long, right? So the entire pipeline ran for about 1 minute and 30 seconds.
2 minutes long video, 1 minute and 30 seconds.
Sorry. I made a mistake. I made a mistake. It ran in about 2.5 hours. Sorry, that was a mistake.
2.5 hours for 2-minute video.
So we designed a solution keeping in mind that during the first FAQ meeting, which was held with BOSCH, we specifically asked a question that how important is the inference time, and we were told that it is not an important metric in this problem statement. And then it was later revealed that tracking the person ID could be a novelty. So to incorporate that into our pipeline, and the retina face-based model is trained on 1 million plus images. So I mean, we tried to produce better results, even if there was a sort of drawback of large inference time, because it was told to us that it is not a too important metric for this case.
Okay. Okay, teammate. Yeah, that's it from my side.
Okay, thank you so much, sir.
Thank you, teammate.